So is my, ooh. Testing my microphone, yes. So we're going to start the session. So thank you so much for coming, and it's so wonderful to be here at this wonderful conference. And there's so many friends and colleagues who are here, including in the audience, who I will probably reference as I go through this, presentation. But I really do want to make it as interactive as possible. So I will leave time for questions and answers at the end. I think we've got about 45 minutes. But if you've got any burning questions as I'm going through the presentation, please just put up your hand and we'll try and answer those questions. So I'll just say a little bit about my work and myself. I know some of you in the audience, so I'm Tina Woods. I wear a few hats. But most of my work over the past sort of 7-8 years has been very, very focused on system change. How do we move what I see as a very broken sort of sick care model, predominantly in the Western world, and how do we move that to a more prevention-based paradigm? And I know prevention has been talked a lot about in this conference today. And I've spent the last few years really working at the cross-section of policy, government, the investment community, the business world, third sector, voluntary organizations, and critically and more, the consumer and sort of public sector. And I'll speak to that a little bit as I go through the presentation on some of the current hats that I'm working at the cutting edge of consumer longevity, health, and wellness. So I think, so just sort of tying together some of the, and so the focus, as you can see in this presentation, is how cities, communities, and clinics can act as test beds for exposomic research and to understand the human exposome and to accelerate aging research. So I'm going to talk a little bit about that, but I just wanted to pull together some of the key strands and threads, sort of what I've been hearing and certainly resonating, I think, in some of the discussions yesterday. So I think a lot of the points yesterday talked really about how do we make sure that all the wonderful science and technology that we're seeing in spades all around the place actually really reaches everybody equitably and justly, so that we can really make sure that longevity dividend sort of reaches everyone around the world. But we do need an enabling regulatory environment to be able to do that, so that came out quite a lot yesterday. And also the need for international collaboration. So I think, often what we find, and although this is changing, is that the science, goes into the silos. And I think that's been one of the issues and one of the challenges to overcome. How do we actually collaborate? There's Michael. I might reference you in the presentation. How do we collaborate better as a scientific community, really to ask the right questions of research, to be able to answer this question: how do we actually really make sure that longevity dividend, that health span, reaches everybody? And the ethics, obviously, behind that are really, really important. It also highlighted the role of governments, and I know some governments around the world, and this is very close to my heart because I'm based in the UK, but obviously do a lot of work internationally, is this whole role of how do we increase working healthy life expectancy, the productivity of our working age populations. I know in the UK, which is where I'm based, I do quite a lot of work at the moment trying to connect up health and economic growth, working with the government. What are the metrics around that? So I'm doing some really interesting work with the Office for National Statistics about how do you measure health linked to economic growth. Because in the UK, as indeed in other parts of the world, we're seeing the dropouts that we're seeing in workforce inactivity rates creating a real drag on economic growth. So these are really serious problems that we're having to face. And I think all of us today, a lot of the work and research and policy developments that we've been talking about today are really, really key to be able to address those questions. And also the economics, and I think the economics of this are really interesting. So that came out a lot in discussion today, and again are part of the reason why some of the work that I'm going to be talking about is so important. Because I think for every year, for example, Andrew Scott, many of you will know, who's a dear friend of mine, he's already calculated, it was in a paper in Nature, that for every year of healthy life expected in the US, that will add 38 trillion to the US economy. Those are big numbers. So I think if nothing else, we've got a burning platform in terms of the chronic ill health that we have as a population, and obviously in many parts of the world, the aging demographic is creating strain on our healthcare systems. We also have that economic argument, which I think will hopefully push the dial on some of the work that we're seeing today. And I was really, really interested in what Philippe Sierra said yesterday about and referencing Luigi Ferrucci's work about the hallmarks of aging. Well, really, we're talking about the hallmarks of life. In that we should really focus on health, not aging and diseases, and how do we connect everything around health outcomes. This, again, is really important in terms of the work that I'm going to be talking about now, and including things like an atlas of biomarkers. So Eric Verdun had mentioned that. So again, these are the sorts of things that will come up in this presentation. So yes, how can cities, communities, and clinics act as test beds for human exposome? And I'll describe what the human exposome is in a second, and aging research. So I have been working a lot with with the ecosystem really around the world in this whole question of the human exposome and how do we accelerate aging research. And I think the really interesting and why I'm so happy to be here is I think the Middle East is a really interesting place at the moment for all sorts of reasons. I think they have the opportunity to really look at health in a very, very different way. And I think these are some of the themes that we're hearing about today. We hear about disruption all the time. Here in the tech world, DeepSeek, for example, has created mayhem, in the last couple of weeks. Well, I think we are poised to disrupt health in a massive way. And I talked about this paradigm of health that needs to move to prevention. Well, I think the Middle East is the perfect test bed to do this because they don't have the legacy systems, the disincentives that at the moment are really hampering progress in the West. So it's a challenge and opportunity to this part of the world to kind of reinvent health in a really interesting way. And I hope some of the ideas that I'm going to be talking about might be able to do that. So many of you will know, and I've talked about the burning platform, how we need to think differently. We need to move towards prevention. And I studied genetics a very long time ago when telomeres were just first started being talked about. So this is a very long time ago. And it was right before the Human Genome Project. And I got really excited about the Human Genome Project. And of course, what we've seen 20 years on is actually more than anything, we have discovered that actually genetics really accounts for a very small proportion of the determinants of our health. It's the epigenetics, it's how we actually interact with our environment that actually is the big picture that we really need to be focused on. So we do need to understand these non-genetic factors better. And we actually have the science and the technology now to run what I'm calling the Human Exposome Project. And so really and this will help us gather that empirical evidence of external exposures spanning the social, psychological, and behavioral aspects of our health, which has been talked about a lot. And in the end, we are talking about human beings. We are not talking about mice. We are talking about humans in this context. And the interaction with those external exposures with our internal biology, our genetics, the epigenetics, physiology, etc., which are encapsulated by this term exposome. Now, this term has really started to generate interest and enthusiasm in the scientific world. It was referenced yesterday. Sebastian, who is here from Nature Agent, he mentioned it yesterday. I was so pleased. And of course, we're hearing more and more about there's more and more research being put out on that. And actually, it really is a very fantastic framework to explain and to show the effects of all these external exposures that happen in our lifetime, across our life course, and even before birth, because your parents' lifestyle, that all has a bearing on the epigenetics and what comes out in future offspring, and how that manifests as chronic diseases, geriatric syndromes, etc., and disability. And I think yesterday, Philippe Sierra just mentioned the increasing focus on functional ability, but because in the end, we need to measure everything in terms of really what matters most to us as individuals, as human beings, in terms of what we want to do with our lives. So, and I think the interesting thing about the exposome is it links everything that we're hearing about in terms of human health, but it also links everything to planetary health. Climate change is all around us. We know this, but we also know, and for the first time at COP28 last year, when I was actually in Abu Dhabi speaking at a Milken Institute event, it was the first time that health was actually on the agenda at COP28. So we clearly know that the root causes and the solutions of poor health are intimately linked with climate. So I think the exposome is a really good framework to actually describe what is going on and how everything in our environments, including the impacts of climate change, etc., are really impacting human health. And I'm talking about collective human health, not just individual human health, because air pollution, if you live and I was recently in Delhi on holiday in India, Delhi, the air, I mean, you can just feel how it's draining your health. And that's something that no one individual can solve on their own. It is a collective health responsibility. So I think the whole discussion really needs to move there. So the seeds for the Human Exposome project were planted a couple of years ago, actually. You see the Lancet paper. Sorry, it's a bit sort of edgy. And we had a huge ream of scientific collaborators on that article, including Nick Palmerini, who's here in the audience here from the National Innovation Center for Aging, who I've been working with very closely on a massive program called the City of Longevity Initiative, where cities, they create ideal environments, really to understand human behavior as they're moving around their lives, and an opportunity to collect data, et cetera, which I'll come on to in a minute. And so we published this paper a couple of years ago. We called it the Quantum Healthy Longevity Innovation Mission, and it's helped us have a lot of discussions with various stakeholders about the need to really harness all the developments in technology around that human exposome, which is essentially was our scientific framework that we put forward in this paper. And I'm very glad to say, and I had mentioned this to Sebastian yesterday, we have had a paper accepted in Nature Medicine about the human exposome project and the need for that, and how cities, communities, and clinics can act as ideal test beds. So that will be published imminently, and really excited about that. And again, had a huge scientific community behind that, showing their support for really moving to Philip Sierra's and Luigi Ferrucci's words, the hallmarks of health. How do you link up all this biology, molecular resilience to health outcomes, and how do our wider environmental exposures relate to that? So just a little bit of a word on what are these sort of factors that we should be aware of in the human exposome. And actually, if you look at the research about exposome factors account for about 80% of our health outcomes. And actually, this term resilience was mentioned yesterday quite a lot, and I think is growing in importance in terms of understanding what it's about, in terms of humans' ability to adapt to stresses in their environments. And when I talk about stresses, it's all these sort of exposures here that I'm talking about. It's everything from the obvious environmental stresses, microplastics, for example, lead. These are all sort of environmental stresses. Air pollution I'd mentioned, sort of particulate matter in the air, NO2, for example. These are really, really massive impacts on our health. But it's also, and we've heard endlessly, and of course know how serious the obesity epidemic is wreaking havoc on our health, and low physical activity levels, all driven by our convenience-led modern-day culture, and primarily from the Western world that is now starting to infect other parts of the world. Sorry to use that very sinister term, but it is true. We are now really sort of victims of a lifestyle that is really, really hampering our health. But actually, it's all the other elements around the sort of psychosocial and emotional side that is just starting to really, really grab everyone's attention. Again, going back, how do we translate all this work that we're seeing in the labs and in animal models into that human understanding? And we know that psychosocial stress, loneliness is the biggest killer of older people, far ahead of even smoking. And we're seeing the impact of mental health issues in our young populations with social media. So the whole importance of communities is really undervalued, and I think is now really starting to gain much more importance in the lexicon of how do we see human health span, resilience, and flourishing. We know, we've heard about the blue zones, and of course there's a whole discussion around the lack of evidence and data really substantiating a lot of the claims around the blue zones. But what we're seeing is that actually some of the key themes from those blue zones are actually all about the exposome. People who live a very long life in these blue zones, they're part of very deeply connected family networks, communities. They look after each other. When you grow older, you're not thrown on the dust heap. You're cared for, you're venerated. These are all really important in terms of the human psychosocial side. And again, when we lack that community sort of fabric and that societal fabric, this is where we're seeing the impacts of psychosocial stress, and actually we're seeing that happening all around the world, and certainly in the UK, we're living and breathing this whole problem of communities really suffering and people living on their own really, really suffering. And of course, their health span is obviously deeply affected. So these are really important exposures. And just some stats. I mean, this is roughly in order of priority, but just some stats here. So for example, the cost of ill health. We talked about how increasing healthy life expectancy adds to the economy, but the cost of poor health, so McKinsey did a report recently, in the US is estimated $2.3 trillion a year. Now that's a big number, right? And globally, I mentioned air pollution. So the World Bank estimates the global cost of air pollution, both ambient and household, is about 8.1 trillion annually. So these are like really big numbers, so we cannot ignore them anymore. And the Exposome provides a framework to get the evidence to create the arguments that can really start to influence government and also investment decision-making, to put money in the right places, to look at health more from an actuarial sort of perspective. Invest here, you'll see the benefit here. Yes, it may take a long time, and this is what has bedeviled us, certainly in the UK and other regions. Government cycles run on short-term cycles, investment cycles short-term. No one's ever looking at the long-term. So this is what we must do. So we know, there's a lot of research, and most Exposome research that you'll see in the scientific literature are drawn from large-scale databases and surveys. And I've talked about resilience, and I've talked about the individual qualities that enable us to be more resilient, which are things around control, a sense of autonomy, optimism. We know that people who tend to be more optimistic tend to live a healthier life. But actually, what's really, I guess, the opportunity is that it's largely unmeasured and unactionable at a personal level at the moment. We're getting more and more technologies to help us do that. And I'm really glad that Jamie's Justice is in the audience, because I know she will probably remember this slide. I was involved, I sit on the, thanks to Jamie, I sit on the Global Enterprise Global Visioneering team, and I pitched the Human Exposome project as a future X Prize. And I went through the process, which was really, really invigorating and great to be working with such amazingly talented people. It didn't make it to the end. Another prize did, XX Prize, Ovarian Aging, which is magnificent because we need that prize as well, so I had no problems with that. But I think, but I was really, really heartened that there is a lot of enthusiasm really about what we're trying to do with measuring the impact of the Exposome on the individual and the technologies that will enable us to do that. So the kind of ideas that we tossed around was, how can we actually use technologies, and that could be part of the prize, to actually capture the data, for example, in a personal Exposome wallet, for example. That could be the idea. And of course, there's a lot of legislation, certainly in the UK, that are looking at individual personal data wallets, for example. Other countries around the world are also looking at that. And how can we pull together that data from all these disparate sort of apps and technologies to fuel a mega research, international research engine and collaboration platform, to give us those insights, to identify the patterns in the data that will really enable us to understand human health at an N=1 level, because that's critical. If you're talking about people, in the end, and if you're seeing people in a clinic, in the end, you are focused on that individual. So that's the real opportunity, is the N=1, but then aggregating that and extrapolating that to a mass population health level to really get those insights that will influence investment policy, the environments in which we're creating. I've been speaking to NEOM, fascinating. They measuring all the data points on an individual in their surroundings, in their environments, kind of like the next generation sort of Framingham study on steroids, to really understand how that will influence the design of homes, neighborhoods, cities, all the stuff that I've been talking about with Nick Palmerini with the City of Longevity program, which is looking at this all around the world, in Buenos Aires and Italy and all these other places in Asia. This is the real opportunity, I think, which hopefully will get more and more attention and investment. So back to the central point of the presentation. How can cities, communities, and clinics offer real-world exposomic test beds, sort of sandboxes? So this is something that we've been tossing around over the last couple of years, and obviously informed how we're thinking about the Human Exposome project. And I think, again, we are at this point when and we talked a lot about how do you translate all the wonderful stuff that we're finding out in the science and the labs, et cetera. How do you translate that into the real world, into the human context, into the whole way in which we design communities, neighborhoods, cities, environments? And this again is where we've been doing a lot of thinking around the City of Longevity program. So we can track people's behaviors. We can track people as they're going through shops. We can restructure, encourage people to take longer routes. We can make it easier to take the stairs rather than an elevator all the time in hotels. These are all the nudges that we need to be thinking about. Redesign, go back, in a way, back to the future. in the way that we design our environments. But then, of course, we've got that data environment. So here is so we've got longevity clinics, communities, cities, and of course, this term longevity as a service. We could be introducing this way of thinking about all the next generation products and services that are all about nudging us, healthier behaviors, healthier beliefs about our health, making it easier. And we're human beings. We need to make stuff easy and convenient in our lives. If it's too difficult, we just won't do it. So it needs to be easy. And it needs also to be cheap. I mean, if we want to really engage, people who don't have it so good, we need to make it accessible to them. So many of you heard about biomarkers. Of course, it's been a topic of huge discussion at this conference. And of course, it's an indicator of normal biological processes, responses to exposures, interventions, etc. So it's a really neat way, and possibly a really neat way to shortcut prevention trials, for example. But we can also use this as a way to actually capture the data and as a huge source of interest. What are the biomarkers that really matter most in terms of us, what matters most to us? We've talked about functional biomarkers. We've got clinical and digital biomarkers now with all the apps. So Michael's here. I mean, Michael knows that I use the Humanity app religiously. He saw me in the gym this morning. And we're both in the same gym. And I use it, and it definitely motivates me to keep on going with that exercise because I can see it's measuring my biological age trajectory, and it's showing that the more physical activity I do, the more I'm reversing my aging process. Well, that's a good incentive. I mean, vanity alone will work for some people, but actually the app, but it's also what it's doing, and this is the opportunity of the world of the future. What it's doing, it is actually capturing a lot of exposomic data because it asks me what my mood is. Have I spent time in nature? It also allows me to upload blood test results. And of course, using AI and all their algorithms, they are able to predict all the patterns that actually really influence people's health. These are the sorts of things that we need much more of, and at scale in cities. This could be used in a city context, in clinics around the world, apps like that. So a little bit of a word on some of the work that I'm just starting to really accelerate in my new role at the International Institute of Longevity, which is a fantastic opportunity to really work with leading clinics around the world. Now, let's face it, the clinics, we're seeing an explosion of clinics. Now, some of them call themselves longevity clinics. I'm speaking to hotels who are all offering so-called longevity, wellness, health. We are seeing, pharmacists. We're seeing, sports clubs. They're all looking at this space of how they can get involved in longevity. There's a lot of interest. And so this opportunity of me working with the International Institute allows us to really work with the cutting-edge organizations, the cutting-edge clinics, those who are really committed to the science. Because what we're seeing is a risk after all the years that we've spent with this industry, this longevity industry, or around Healthspan, I know is the term that we are using very much in this conference. We are now at the risk of introducing reputational damage if we don't get this right, if we don't have the science backing up the protocols, the guidelines, the way in which we do things, to protect the consumer, to not waste their money, and needlessly, and we're already starting to see articles about overprescribing with supplements. So we are at a very, very important time in this industry to really get it right. And so, and we also have to remember that, going back to my earlier point about the wider determinants of health and the exposome, we cannot ignore the fact that if you are poor, if you don't have good education, if you're disadvantaged, automatically that takes 10 years off your life, no matter. And so we do have to address that as a community. And I think I call out to those with the resources, with those who can afford to go to these clinics, who are getting the best diagnostics, the best interventions. Let's use that research for the benefit of everybody in this global sort of scientific endeavor that is really, I think, the challenge and the opportunity, and actually is a responsibility for all of us as global citizens. And that's some of the work that I want to do with the International Institute. And so just the mission statement there, to drive global excellence in longevity through responsible medicine, adaptation research into practical use, and promoting best practice to extend human health span, resilience, and flourishing, which is the really important point. So that's a very busy slide, and I'm not going to go through it in detail. But what I do want to say is just a few things. I don't know if my colleagues are here. I don't see. So the Institute has been around for a few years, actually, and it was founded by Joanna Bench and Eric Verdun. Two names who I think Eric was on a session this morning, of course, was there at the session yesterday, and Joanna Bench was also on a panel. So Joanna runs Longevity Center Europe, and of course, many of you will know Eric Verdun is the head of the Buck Institute. So they set up the Institute, this institute, a few years ago, and I've been brought in to kind of accelerate and focus the program. And really accelerate this at an important point of our industry, some of the things that we want to do. Via the think tank in particular. So, but it's actually more of a do tank, and people who know me, I'm into getting things done, hustling, getting action done. And that's really the aim of bringing that thinking, but it's into the doing. And I think, and really working with a supportive network of collaborators around the world. Coming together to address the medical and business challenges, and to support research in patient trials, in decentralized clinical trials, harnessing all the incredible advances that we're seeing with AI, genomics, et cetera, and personalized medicine. So a little word, we actually ran a bit of a survey, and I'm just looking at the time. I've got about 15 more minutes, haven't I? Yeah. We ran a survey, actually, with some of the cutting-edge clinics around the world a couple of months ago, which fed into the roundtable of longevity clinics that was held at the Buck Institute in December. Because we asked the clinics, like, if we were to come together, knowing that the clinics, obviously, in a way, I mean, they're commercial entities, they have their own niche, they compete for customers, so there is this sort of competitive element. But actually, what they've also realized is that there's a huge added value and a benefit of coming together on the research front in terms of the standards and the protocols that we need to be developing internationally, et cetera. So we asked them, how should we be working together in this environment to collaborate, to really spur on scientific progress? So we sort of badged it as the Global Alliance of Longevity Clinics as a starting point to really get clinics around the world coming together. And so what we found, and this is not a huge, large-scale survey, but actually we're now starting to look at much bigger surveys. What do they consider important? Now, of course, international industry standards and best practice is hugely important. About 90% of them said absolutely. And in terms of the priorities, what came out tops was patient care and safety protocols. Because again, going back to my point earlier about this point that we are risking reputational damage in the industry, and of course the ethical principles and the guidelines underpinning all that is crucial. And I think the other point that really came up, which is really interesting, is, how do we pay for all this? There's a lot of money, but let's make sure, and this is where business model innovation, new investment models, and new ways of looking at this, the kind of the actuarial model for health that, of course, insurers are looking at, but are a little bit behind the curve in this. How will this actually influence business model innovation? How can we make it pay for prevention? We know that people who've got it good, who've got the resources, they can, get their full diagnostic workups, get all the best care in the world. But how do we actually move it into a place where everyone can benefit, where there are ways in which, we can incentivize, and this comes down to new investment incentives, but also business model sort of innovation. Looking at the insurance industry, for example, how can we actually make it pay? So these are all the sorts of things, because as a clinic, if you had insurers, reimbursing for prevention and for diagnostic tests, obviously that opens up the whole opportunity for other people to benefit from all of this technology. So these are all the things that we really must look at. But equally, technology standards. How do we share data? How do we actually do what Michael Gear is doing with Humanity App and many other solutions providers? How do we make it easier to actually gather that data, which is already being gathered by patients, and people in the clinics? How do we do that? And what are the standards around that? Yes, and we do need internationally recognized policies, et cetera, and regulations. I talked about system change towards prevention. We also need to be working with governments and looking at, how do they need to be seeing all this, so that at the moment, for example, in the UK, we've got a lot of government focus, obviously, on rescuing our very understrapped NHS and care system. But so how do we actually deal with the short term, the crisis that we're facing with this model of care, which is getting more and more demand of the aging demographic and poor health. So how do we actually make sure that there's money left to invest in that prevention space? So I think we do need to work with governments. And again, I come back to the Middle East, where we're seeing an opportunity to really reinvent how we see health, and making sure that the regulation actually supports that, to invest in prevention, to keep people healthier. The numbers speak for themselves. If you have a healthy 65-year-old who is still potentially working, still active in their communities, still spending money into the economy, it's a no-brainer. The numbers just add up. Stop waiting until we're sick. Invest in prevention, keep us healthier. This is where we must go, and this is where the opportunity is for us to come together. Yes, and of course, just going back, why we see the clinics being critical as an opportunity for a test bed for the Human Exposome project. They know that there is a huge opportunity to collaborate in key research projects that may not be getting the attention at the moment. I talked about this new frontier of longevity, sleep, mental health, even psychedelic medicine. These are all the areas that longevity is looking at. It needs more research, more trials. And again, going back to that point, in the end, we have to be governed. What really matters to human beings? What is their incentive and their motivation to keep living a healthy, long life? We have to understand that, and that has to be reflected in the studies that we undertake in research. And again, the clinics, they provide a fantastic opportunity. They have got their patients. Yes, generally those who are better resourced, but there are more and more clinics who we want to work with who are what we call the Hyundais and not the Mercedes-Benz. They are trying to reach out, and going back to Joanna's clinic in Warsaw, they are at a price point that is well below many other clinics. This is where we need to go. And of course, we need really good training. Now, Andrea Mayer, who many of you know, and people like Evelyn Bischoff, they're doing excellent work with the HLMS Medical Society, which is very, very focused on medical training, clinical standards. Abu Dhabi, we, as many of you know, will have, it's actually mandated from a regulatory point of view for clinics to follow these standards. So actually, there's some great work. We want to support and accelerate and promote that work. We also want to look at these sort of, I guess, the grayer areas, sleep and food and all these other areas, which may not be the domain of medical longevity clinicians, but actually when you're looking at the whole plethora of people involved in what I call the customer journey, the person who may, if you're visiting a hotel and getting some longevity service there, that's one point in time. We need to have a full understanding of the customer journey. When they first get diagnosed, how you track and manage them throughout their health journey and keep on following up, that is really important. And making sure that you are able to track and help that person through their journey of health and keep them healthy. So understanding that is very much at the heart of where we need better training, all the other allied healthcare professionals, the sports coaches, the nutritionists, the functional medicine specialists. These are all really important part of the fabric. So again, that training needs to reach those areas. And of course, personalized medicine. I think, people who know Leroy Hood, and we've got Michael Sagner, who's going to be helping us on the board. The 4 Ps, medicine, participatory, personalized, personal. These are all the really important points that we need to really focus on. And of course, advanced diagnostics and this whole biomarker space. Now, there are a few groups around the world, Biomarkers of Aging Consortium. We've got a group in China looking at this. There's excellent work on really looking at biomarkers, and of course, we know about all the aging clocks. There's those used in research. I spoke at the Biomarkers of Aging Consortium at Harvard a couple of months ago. There are hundreds of clocks. Organ clocks, molecular clocks. There are clocks everywhere, aging tests. So there's a massive focus on those. And of course, there's research, there's a clinical setting, but what we must do is how we are actually going to use all those different tests, all those biomarker tests, aging clocks, aging tests. How are we actually going to decide which ones actually really are important for the individual, because it might be different, and actually use that to track progress. So there's a massive focus there that we need much better collaboration around. And yes, obvious, integration of technology in key areas, sharing trends, diagnostic interventions. I mean, there's a whole talk about interoperability, but I think there are also other ways that we can actually look at patterns and data sets, which again is where we can use the WYSI technologies. And of course, we must promote all the different sensors, the wearables, et cetera, because they all are opportunities to capture in a passive way, what's happening in our lives. And even looking at, for example, in Abu Dhabi, for example, every building is built to the IWBI standard, for air quality in buildings. And they're collecting that data, and they know what impacts human health. So we've got increasing tools to really enable us to understand health. And of course, predictive models as well. And of course, and this is the final slide, I think, before I'll open up for questions, there's a massive interest in collaboration. We still have a very, very cooperative community. Let's use that. I talked about competition. Yes, we can have healthy co-opetition. That's also really important. And of course, networking, et cetera. So these are all the things that we'll be looking at. And working with, opportunities here at Hevolution. So I'm going to stop there just to open up for questions. And I think we've got about 7 minutes left. But yeah, so hopefully that was helpful. But yes, I encourage all of you to get involved. Certainly come speak with me. I would love to work with anyone who's interested in the International Institute and also the Human Exposome project, which has feet outside the Institute as well in terms of opportunities working with people like Nick and the City of Longevity program. But I see the Middle East as being a really interesting opportunity to look at that in a way that is more difficult for other countries around the world who have much more snarled up systems and incentives that make it more difficult to actually really be bold and pioneering and fast, which I always like to do. So anyway, open up for questions, please. Anyone? So I see one here. I'll just go there first and then Nick, 'cause I know you, Nick, so I can open.
Thank you so much for this inspiring presentation, Tina. And so in one of the early sessions, Eric mentioned that there are psychological barriers that prevent people from adopting healthy habits.
Yes.
And what resources or strategies have you found effective in addressing psychosocial stressors, especially around social isolation and loneliness?
So that's a very interesting question. And of course, in the end, we're talking about real people, individuals who have circumstances, who live in environments and whose behaviors and choices and beliefs are so influenced by their environment. So I think there's a whole cultural context that one has to understand. It's very different around different parts of the world. I mean, many of you know that Singapore are kind of light years ahead of many countries in terms of how they've seen the aging demographic as an opportunity rather than just as a challenge and as something really difficult. What they've seen, and I think this is part of the point, is they see, and this is where policy and government have really gotten involved, they have seen and have focused their policy on celebrating an older life and making it easier for people to keep healthy and to be active citizens in their communities, but also enabling people to stay together. So I was really interested in some of the policies that enable, for example, young people to live closer to their parents and grandparents. It's things like that. It's about how do you actually incentivize the fabric of society? And if you look back, I mean, civilizations of old, I mean, we are social animals who thrive best in our families, in deeply connected communities. So I think, I think that's a really important part of the puzzle. I think this is where governments need to support that. And it's not about individual agency, because often when you come to conferences about the science, it's always talked about in terms of like what app or what will help the individual. I think we've reached a whole new tipping point. It has to be about the collective health responsibility of governments working with business, working with citizens. In the end, our behaviors impact others, So I think we've reached that point. So I think individual, and I think actually going back at the N=1 level, in the end, you have to understand the intrinsic motivations of people. Why? And we need to focus on not the question of living healthier for longer, but what is it for people to want to live healthier for longer? That's the fundamental question. And it's about hope, it's about aspiration, it's about joy. I would love to do a trial on how joy and hope will add years to your life, because I think it's a fundamental human need, which you don't get in animal studies, So I think these are really important to understand. And I think we can do that. We can incentivize and encourage and nudge positive behaviors at individual level in the way that we design our environments, and making healthy food easier and more accessible and not so expensive, and making junk food more difficult to get. I think there's a whole issue around the food lobby, and I have to say, no matter what you think about Trump, I think the fact that he's taken on the food lobby is quite an interesting one, actually, because obesity is killing us. It really is, and I'm afraid all these fancy sort of, Ozempic drugs and all the rest of it may not necessarily be the answer. It's one part of the solution, but it's not the only solution. We have to look at the environments in which we live. And let's face it, not all those drugs are going to be accessible to all of humanity. So we have to look at the root causes. So I hope that answers a little bit of your question. Nick.
I know you have a few minutes. Great. Thanks for the fantastic presentation, Tina. One question. I see the clinics becoming the primary care of the future, probably. Mm-hmm. How you see this process of democratization of the clinics becoming maybe the hub through which you then can create this kind of a testbed?
So I think, let's face it, at the moment, this huge focus and investment and, dare I say, gold rush, which we are seeing, everyone piling in. Now that's great. It shows that everyone is, and we know that the health and wellness industry is just booming. There's a load of investment, and for all the right reasons, which is great, because that's part of the system change that we need. We need the consumer and the public to be on side with this, because in the end, we vote in the governments and all the rest of it. And so I think that the challenge is how do we actually make sure that the knowledge that we're gaining through the data and through the trials that may be easier to do in the context of some of the work that we're trying to do with the International Institute in terms of running trials with all the clinics who have the patients, the paying customer, the clients who are actually participating in this. How do we make sure that the benefits and the insights and the knowledge, they hit governments in a language that will resonate and show? And because again, people who are smart, they've done the numbers. If you invest here, if you prevent ill health, and you reduce this increasing sort of demand that at the moment is bedeviling our healthcare systems, the numbers will speak for themselves, but we need the evidence. So I think if we can get the evidence and the arguments in a way that the policymakers, and I spend a lot of my life, as you know, Nick, speaking to the policymakers and the government officials, and who all, as scientists, we all need to keep educated. I mean, it's endlessly complex, the stuff that we're finding out every day now in longevity research. Being able to communicate that in a language, but with the evidence that will really start to influence decision-making with the policymakers, who in the end are going to make the decisions on making it more accessible to people who might then support, for example, the insurers and business models and all the rest of it, and support. I often talk about health into ESG investment, that support the pension funds and the institutional investors with, how do we make it more attractive, to invest in health, which is linked, let's face it, to the climate change agenda. We've got ESG. Well, and I know there's been lots of criticism and issues around ESG, but let's make it work as an entire proposition, the 2-for-1 approach. Invest in health, invest in planetary health, the climate, and you get the full benefit. But we need to make it easier, and we need the business models and incentives. It's all about the incentive structures. That's what we need to change. Yeah.
Thank you. I have loved your presentation, and everything resonates. I am an architect, and I'm bringing IWBI and DALIS to Saudi Arabia with a local regional headquarters.
Wonderful.
And the Mayo Clinic has been instrumental in our work in terms of building an understanding between the building science and human health sciences.
Yes.
Are you familiar with any other global institutions that you've worked with that are really dedicated to doing that in the Middle East?
So, specifically reference to Middle East, not specifically, although I see Ahmed, who might be good to speak with actually, because he's very interested in this whole agenda, from the Chaos Institute. I know there are many organizations working at a global level, like the Global Wellness Institute, hugely committed, and we've got many other organizations looking at, for example, happiness, and there are so many organizations all looking at environments for human flourishing and happiness and thriving. So I think, but in answer specifically to Saudi Arabia, not more than what I know about IWBI, which is obviously doing amazing work around the world and have gotten incredible evidence. But I think, and I don't know, Nick, do you know? You might know. So this is, in terms of the built environment in Saudi Arabia, whether there are any other organizations, because I know you've been working quite a lot.
As far as I know, there are many there just pushing forward to this kind of a concept of, enhanced type of kind of lifestyles. There are neighborhoods, as you mentioned before, there are hotels which are now designing, embedded in the hotels, this idea of the quote longevity buildings or healthspan buildings, depending on the narratives. So I think there's a full practice of architecture making it happen, and also how this architecture is more connected to the environment. I'm working with architect Stefano Boeri, which is the inventor of the vertical forest, and they're developing the idea of vertical forest for the environment of the Middle East, for example, which is not vertical, is horizontal to provide shades, but the concept is the same, so that you have buildings that themselves participate in, let me say, reducing or impacting the exposome, as Tina was saying before. So I think there is an incredible, let me say, layer around the World Health Span that is touching even practice that not necessarily seem to be so directly connected, why they are, because bringing forward the narrative that Tina is suggesting, so we see the things from the world perspective, allow us to see every single sector and every industry to be part of the play.
But I think you bring a very interesting point, because some of the stuff that I think architects are a little bit behind the curve, certainly in the UK, for example. So, and that's partly to do with the incentives for housing. And the fact is that we need to start looking at how do we create health-first housing. So, because a lot of the housing developers and the builders are very sort of profit-driven and margin-driven and what have you. And so, and again, this is where the governments need to be on side and policy, because we need health-first buildings. I mean, and health equity first, so social housing and all the rest of it. So this is all the stuff that we're talking about at the moment with my sort of the hat that I wear when I'm in the UK, because you need that. That's where policy and governments have to be on side, and it comes down to the incentive structures, in the end. Yeah. Time up, I guess. Well, thank you so much for coming. And do speak to me if you want to get involved in some of the work that we're doing. So, yeah, thanks.
Good afternoon, everyone. Welcome to the second season of Global Healthspan Summit. My name is Dr. Bashair Al-Mubarak. I am the Director of Scientific Research at Hevolution Foundation. We hope that you are actually having an engaging and fruitful time and experience so far. In this session, we are delighted and excited to host two of the most distinguished researchers and scientists in the field of aging biology. Their research, their work has paved the way for so many other researchers in the field. Today we're actually hosting both Professor Vadim Gladyshev and Dr. Steve Howarth. We'll start with the talk delivered by Dr. Vadim Gladyshev. Dr. Vadim research focus actually spans a wide area, which includes redox biology. Also, it includes the regulation of aging and lifespan with over 400 publications. Professor Vadim and his team have contributed to advancing our knowledge and understanding of the molecular basis of aging. Professor Vadim, as a leading expert in the area of biomarkers of aging, serves on the scientific committee of the Consortium of Biomarkers of Aging, which is a collective effort and a driving force towards developing and discovering robust and reliable biomarkers of aging. And in addition to his well and renowned research, Professor Vadim also holds a number of distinguished positions, including the director of the Center for Redox Medicine at Brigham Women's Hospital and also a member of the faculty team at the Broad Institute. I would like to invite you all to give a warm welcome with a round of applause to Professor Vadim. Welcome, Professor.
Thank you, Bashair, for the kind invitation and for the great introduction. Thank you very much. And it's an honor to be here and also share the stage with Steve Horvath, who will be the next speaker. So actually, last year at the same meeting, I gave a talk about a year ago. It was a full room on biomarkers, and now it's again. So thank you very much for coming. So, and because it was a presentation just a year ago, I will basically talk about new stuff. New research that was done since then, or give you some updates. And also just to mention, because I presumably Steve will talk mostly on epigenetic clocks, I will talk very little on epigenetic clocks in my talk, so that we have a complementary thing. But the session is biomarkers, right track or new track. It's a very important topic, I think, in the aging field, and to me, maybe the most important development in this century, actually. So in the field. So first, we need to understand that the advance that we have in biomarkers is the ability to quantify aging, right? But what is actually aging? Aging is viewed in many different ways by different people, and this is also highlighted in many talks at this conference. For some people, this may be chance of dying, increased chance of dying. Some people say, no, it's actually a functional decline, which is aging. Some other people, it's a damage accumulation, and so on. And depending on that views, which are different in different people, we could differently quantify biological age, and differently quantify aging. So we can do it, for example, by quantifying chance of dying, and we can train clocks that quantify that time to death. This would be similar, for example, to Steve's like a Grim age clock. Or we could quantify the incidence of diseases, so-called health span. Or we could quantify functional decline, like VO2 max or whatever, some other features. Or we could quantify damage accumulation. Or we could quantify rate of change, like something which would like Dunedin pace clock. They are all different manifestations of the aging process that can be quantified by this clock. But which one is better? There is no currently consensus in the field. So for this, we formed a consortium, Biomarker of Aging Consortium, about 2 years ago. And this is a large group of people. For example, we had a meeting just 2 months ago, which was attended by 450 people from more than 30 countries. It's a huge interest in the field currently. This is just some of the faces that really a huge crowd of people. This is the first paper we published as a group This was about a year and a half ago. Since then, there have been many other papers published. There's in Cell and Nature Medicine, there's Nature Aging, and several other studies. So we also, at the last meeting, we ran a competition. We call it challenge, where we collected 500 samples from people in our Mass General Brigham Biobank who donated samples maybe 10, 15 years ago. And we profiled them through DNA methylation and then asked anybody just to compete and tell us what's the age of these people. Or like how much time to death may be expected, because some of them died, so it can be calculated. And there are many teams who competed, and we announced two winners, two phases of winners for prediction chronological age or predicting time to death. And this you can see, like this is the chronological age prediction. 37 teams competed, the 500 submissions. These are existing clocks, and these are new clocks. This is mean absolute error. It's quite remarkable that newcomers, new talent come and develop clocks that outperform the best clocks currently in the field. With mean absolute error almost like approaching 2 years. It's quite remarkable. And these are some of the three winners. This is actual age, and this is predicted age. You can see there is amazing correspondence. So this means that this chronological age can be predicted very accurately, even with one model clocks, like only epigenetic clocks. But of course, if we talk about multi-modal, combining different omic modalities, it's going to be even better. And also for prediction time to death, also actually the clocks of the winners outperformed the existing clocks. So now I'd like to highlight a few recent advances that we had. So this is the study that was published by Jesse Paganik, who is a junior faculty in our lab, and he found that severe stress reversibly changes biological age. So here we described several types of stress, and now we have more. So where like major surgery, for example, or like pregnancy or parabiosis reversibly change biological age, meaning that adversity, severe adversity, literally makes organisms older. And once adversity goes away, biological age is reduced. There is some other models, for example, severe sleep deprivation also reversibly changes biological age. Also, just very quickly mention two studies we published within the last year, both in Nature Aging. One is by Albert Ying, who is a very talented graduate student in the lab. He developed the first causal epigenetic clocks. Because the problem with many clocks that currently we have is that with age, everything kind of changes. There is, for example, damage accumulates, but organism also responds to damage by activating protective systems. And these protective systems also have age-related structure, and therefore they end up being part of the clock. But when we subject animals to intervention, or humans in this case, we don't know which part of the clock we target. So this causality is very important. So Albert was able to separate into damaging changes and adaptive changes and build clocks separately for them. And so now there's many applications of this clock. And Andrei, he actually found this stochastic component of aging, which is very difficult to quantify by existing clocks, because there's a kind of almost like random changes across the cells and tissues. And this was made possible by comparatively analyzing single-cell DNA methylation versus bulk DNA methylation. In the same issue of Nature Aging, there were two other studies on the same topic, one from Björn Schumacher and the other one from Andrew Tischendorf, but with the same conclusions, similar conclusions. Now I'd like to talk about a different type of clock. This is transcriptomic clock. This is still an unpublished study, and this was developed by Alex Tishkovsky, who is also junior faculty in our lab. And this one, he collected almost 5,000 samples of RNA-seq across animals, like mice and rats, under conditions under which we know their lifespan. So, for example, we sequenced many of the samples from the intervention staging program of the NIA, and also collected metadata for many other models where lifespan was increased by interventions or decreased. You have for progeria models, for example, lifestyle, dietary, drugs, and so on. And he developed a clock for transcriptomic age, for first trend for chronological age, and this is the clock. The actual age, predicted age, works really well here in a training set and test set. And importantly, he also developed clock based on on mortality, time to death. And this is the clock here, also works really well. And this is application of the clock to existing, to known interventions. These are lifespan shortening interventions actually make the age higher, and lifespan extending interventions make age slower. So this immediately suggests that this type of clock can be used to test and identify new interventions. So as a result, now we have numerous collaborations of using this clock, because everybody is interested, because there is so many RNA-seq data sets, and it's very easy to apply both in the bulk manner and also in a single cell manner. So this is one application of this clock where we apply this to diseased tissues. In many models of disease in mice, we have like Alzheimer's disease model, some heart disease, ischemic disease, and so on, kidney disease. In each case, diseased tissue is older than control. It's very interesting observation. Now, I'd like to very quickly mention, this is still ongoing work, where we've identified, using the clocks that we have, we identified embryonic rejuvenation. We found that there is a natural process for rejuvenation that happens during development, early development. We initially found in mice, and then in humans, and also observed in frogs. And this work was done by Csaba Kiripesi, who now has his own lab in Hungary, and also Alex Trapp, who now leads bioinformatics at the company Retro. And this is what we found here, initially through epigenetic clock and later transcriptomic clock. Now I'd like to switch gears to talk about organ-specific aging. This is another very recent development in the field. And one paper you might have seen is a paper from Tony Viscaray, published about a year ago in Nature, where he analyzed somologic data set data and identified proteins that released from various organs to plasma, and through this way he was able to tell about aging of different organs. So in our case, we also analyzed, but we used UK Biobank data, and this was done by Ludger Gumin, who is a postdoctoral fellow in the lab. And he trained clock for chronological age. This is the actual age, and this is predicted age for men and women in different color. You can see there is very good correspondence. And this is clock trained on time to death. Very often we find that mortality clocks outperform when we talk about diseases. So now we often talk about what's the age of the organism and how particular interventions can improve like well-being or health span for organisms. And actually most talks here at the conference talk about this. But if you think this way, organisms composed of different organs and systems, they might have slightly different ages. They have their internal clocks everywhere, in the brain, in the heart, in the lung, in the kidney, and might be unequally aging. How can we describe this diversity in aging patterns? So we used initially the approach of Tony Viscaray, except we trained our clock for mortality in a much larger data set. Based on the profiles of 3,000 proteins on Olink platform, and we identified first proteins that come to plasma from different organs. Like we found proteins which, like made in the brain, go to plasma, made in the liver, go to plasma, made in the kidney, go to plasma. And once we know these proteins, we can trace age-related changes and develop clock trained on future mortality, time to death for each organ. Yeah? Now we have organ-specific mortality clocks based on plasma proteins. And then this slide shows residuals of these clocks. Yeah? So basically we can relate, if somebody is like older in the brain, they would be also in the liver. Like older in the artery, also like older in the brain. So it's reasonable. Sometimes organisms age more, and all of their organs kind of show accelerated aging. And this is for chronological age, and this is for mortality, the same. But now if we take, for example, a lung-specific model, it's a mortality model trained for the lung proteins that come to plasma, right? And ask a question, which diseases are predicted best? COPD is predicted best. It's a lung disease. So lung model predicts lung disease. The liver model predicts liver disease, liver cirrhosis. So if we now cluster based on different organ clocks and different diseases, we also find very interesting observations. For example, we look at people with dementia. Their aging of the intestine, kidney, artery, okay, normal, like good age, but then they are older in the brain. People with COPD, they're older in the lung, and so on. So consistently, we observe that organs that develop diseases, they are older, literally older than other organs. Now, we can look at associations, these organ clocks. So everybody knows that smoking is bad. Don't smoke, yeah? But then, which organs are affected? So we look now here at the effect of smoking on organ clocks. And basically, it shows that smoking accelerates aging in all of the systems. But lung is actually targeted more than other organs. Again, it's very reasonable. Now, how about alcohol consumption? Alcohol consumption is considered to be not healthy. But does it equally affect different organ aging? So we find that it's not. So for example, kidney is really affected by alcohol greatly, and intestinal aging as well. But for example, aging of the artery is not. Artery is more like rejuvenated by alcohol. It's really very interesting. So, and just another illustration of that. Let's say we take the clock in the artery, yeah? And look at the effect of wine and yogurt. Wine has a positive effect, and yogurt is negative effect, even though we consider yogurt is good. Now, if you look at the same diets, but look at the intestinal aging, it's reversed. Wine is bad, yogurt is good. What this means is that depending on particular aging patterns of the organism, we need different interventions for different people. To me, there is not going to be a universal intervention, because even things like calorie restriction or rapamycin might be helpful for some people, but would be damaging, deleterious for other people. We need to understand how a particular organism ages and identify personalized interventions for that organism. Now, because we use this amazing data set, we also developed very focused panels for predicting major diseases. So we identified a panel of 21 proteins, which can very nicely predict 6 major diseases as well as mortality. And this is an analysis of the data. So for example, if you analyze, if we use all O-link data for 2,900 proteins, it's like C-index is like that. And you can see hazard ratio. But actually, 21 proteins almost as good predict these patterns. And it's actually better than, for example, pheno-age or individual proteins, of course, better than age as well. These are the proteins. They come from different organs. And so, like these particular proteins, for example, are best predictive of brain diseases and brain mortality. And these proteins are best predictive of the liver disease and mortality, and so on. And these proteins are best predictive of mortality of the organism. Particularly GDF15 is really amazing protein in predicting mortality across the board. So this is also application of these clocks to many diseases. You can see nicely predict. Way better than clinical biomarkers currently in use. Way better. And also, for comparison, this is the Calico data from Milamut et al. And actually, they developed clock-based models based on 14 proteins. Our 21 model protein, I think, works better in most diseases. And you can see this data also here for many diseases. So we hope that panel will find many users, because with only 21 proteins can be nicely predicted future disease incidents. So what all these findings tell us? They tell us that there is asynchrony in organ aging. And perhaps it would make sense to target weak links, which are the organs with accelerated aging. We need to think of personalized longevity interventions. This is how we think it works. So aging begins somewhere here, and all organs age somewhat in a similar way, but some organs age more, like in this case, heart. But it's not a simply more aged organ. That organ also interacts with other organs. So it's aged and also altered. It's in a different state, and it's so far very difficult to describe that state. So is aging a disease? That's the question that is discussed here often. We published a paper about 8 years ago where we claim it's actually a bad question. The aging is not disease and not a disease. That's what we think. But the question can be reversed itself, and we can ask a question whether disease is aging. And I think the data that so far suggests that disease, chronic disease, like heart disease, Alzheimer's disease, diabetes, may be viewed as accelerated, altered aging of particular subsets of the organism, so-called systemic aging, or aging. Diseases can be viewed as a pockets of non-autonomous aging. So that's it. So this is what I will told you today. So about a little bit of Bayesian biomarkers. Biomarkers can be done, can be used at the bulk level, single cell level. There's now causal biomarkers, multi-tissue, epigenetic, transcriptomic, proteomic, but of course other modalities as well. I told you a little bit about reversible changes in biological, and also about biomarker of aging consortium and challenge. Also a little bit about rejuvenation. I mentioned about embryonic rejuvenation. Of course, Yamanaka factor is also very, very nice. And another news is that this organ-specific aging, they're very excited about that. Models can be built based on chronological age, mortality, and there is a nice association with diseases and diet, and suggests that diseases themselves may be viewed as pockets of non-autonomous aging. But of course, our goal in the lab is try to better understand aging disease and eventually target it, because I think we're still at the beginning in this long road. And finally, this is an acknowledgement. This is a current lab that many of these people contribute this work, as well as previous lab members. We have many collaborations and funding sources. Of course, I'm very particularly grateful to Hevolution, who funds some of this work. And I would like to thank you for your attention. So I think we suggest that Steve will present, right? And then we will have questions. Yeah. Yeah.
Thank you very much. Our next speaker is Dr. Steve Horvath. Dr. Steve Horvath pioneered work in terms of the epigenetics of aging, which actually reshaped our understanding of aging with regard to this aspect. He leads a huge research group at Altus Lab, and his research is at the intersection of many, many areas, including, of course, the epigenetics, biomarkers of aging, epidemiology, genomics, comparative biology. And Dr. Horvath and his team were the leaders in identifying the first set of epigenetic clocks to measure the aging process in human. And in their most recent work, they've also identified a group of clocks that could have a universal application across mammals. And the work from Dr. Horvath group also continues to be recognized worldwide and to influence the research in aging. A round of applause, welcoming Dr. Horvath. Welcome, Dr. Horvath.
Thank you so much. Thank you. It's a real pleasure to speak here. I will talk about my favorite topic, epigenetic clocks. But before I do that, I want to say I really love proteomics clocks. I love everything Vadim presented. I think it's phenomenal. I just have one focus here, you know. I'll start with something many of you know. Epigenetics relates to many chemical modifications. I, of course, focus a lot on cytosine methylation, but there are other modifications, most importantly histone modifications, and these epigenetic modifications determine whether certain genes are turned on or turned off. And many people have asked, well, develop an epigenetic clock based on histone marks. And by the way, why? Because certain exciting species don't even have cytosine methylation. C. elegans doesn't have cytosine methylation. Drosophila, the fly, doesn't have cytosine methylation. So arguably, if you look at histone marks, probably you can build clocks in these species. And it turns out, this is a study by Lucas Paulo de Lima, who described human epigenetic clocks based on all histone marks that are exciting to people. H3K4, H3K27, H3K9, pretty much all of them. And it works quite well. It's based on ChIP-seq data. As I mentioned, I will focus on cytosine methylation today. And just to remind the audience, we published a paper on Grim age a couple of years ago. And this paper describes a mortality risk predictor, time to death, based on covariates, again, methylation covariates, but they're interpretable. For example, a methylation estimate of smoking pack years, a methylation estimate of GDF15. Vadim just talked about GDF15. One can estimate the levels of GDF15 based on cytosine methylation. So anyway, we have this mortality risk predictor. And one thing I briefly want to mention, the methylation estimator of smoking pack years is actually more predictive of mortality risk than self-reported smoking pack years. And the statement also applies to several other proteins, not all of them though. Now, we call it Grim age because it does predict mortality, as Grim age as in Grim Reaper. So here the curves show in red the 20th percentile of fastest agers, and in blue the 20th percentile of slowest agers according to Grim age. And you see a pretty good separation when we look at different racial groups and different genders. And this Grim age has been very carefully validated really in all racial groups and all strata. We know that, but what's new? What is the new frontier for methylation biomarkers, but more generally all biomarkers of aging? We really need longitudinal studies. Why? It has a lot to do with causality, establishing causality. And one way to indirectly address the issue of causality is to look at the rate of epigenetic aging. So assume you have multiple blood draws and you estimate the rate of change of Grim age. You want to ask, is that rate predictive of health span or lifespan? And so fortunately, Luigi Ferrucci and Pei-Lun Kuo really looked at this in an Italian cohort. Only 699 people, not very large, but they evaluated whether this longitudinal rate of change is predictive of time to death. And it is, you know, many of these clocks, especially Grim age, but also Dunedin, they show that expected pattern. So that's indirect evidence that these methylation clocks are predictive of future events and that there's a causal link. The best approach for establishing causality is clearly a randomized clinical trials, or more generally, interventions. And that's why Vadim highlighted the utility of the mouse studies, for example. In humans, we have far fewer validated interventions. But let's talk about what interventions are known to affect epigenetic clocks. Pretty much healthy lifestyle. Anything you know about avoiding obesity, metabolic syndrome, and so on relates. And here's a little study that's quite interesting, where Zsolt Radak, a professor in Budapest, Hungary, carefully looked at Olympic champions. And he found an interesting result, which is people who won a medal less than 10 years ago at the Olympiad, their Grim age was reduced. Okay, so meaning exercise is good for you. However, people who won a medal more than 10 years ago, they had normalized, you know. So I don't know what happened. Did they turn into couch potatoes, you know? It may relate to what Vadim described. There is a response, but it bounces back. And by the way, this is a problem with many, many rejuvenating interventions. They are transient, unfortunately, you know. Now I want to come to another topic, omega-3 supplements. Back in 2018, Arkelu in the lab showed that self-reported omega-3 intake correlates negatively with grim age. Now that's an observational study in the Framingham Heart Study. Observational studies are famously fraud. But anyways, it was interesting, you know, and p-value was very good. Now, fast forward, I think 2 days ago, we published a paper where Heike Bischoff-Ferrari, who's a clinician scientist, conducted a randomized control trial, very rigorous, in a Swiss cohort where people who were 70 years or older, average age 75, took 1 gram of omega-3, and it was a very rigorous randomized study, meaning people got pills where they didn't know what's in it, you know. Anyways, and so these 70-year-plus individuals were followed for 3 years, and the question was there a change, baseline versus 3-year follow-up? And the interesting thing is, so yes, there was a change. So here I show you the pheno age clock, but more importantly, the grim age clock. And you see the people who took the omega-3 versus the placebo, they did have a benefit, slight benefit. I mean, this is not the cure against aging, you know, but it's, so quantitatively, it rejuvenates you by a few months, you know, so it's, but in any event, it was kind of reassuring because I, for one, take these supplements. But what made this study exciting was that there were other interventions, vitamin D, which many of us take, and also some home exercise tests, not much, like exercise a little bit 3 times a week. And there was, at least at the level of pheno age, an additive effect, you know, so it's kind of a nice study, you know. So that's about these clocks, grim age and pheno age. But remember, I told you, grim age is comprised of surrogate markers for plasma proteins. And remember, my favorite plasma marker is GDF15. And again, this is now a methylation estimate of GDF15. And look what we find. So yes, again, omega-3 reduces it. But what we really see is that there's a pretty strong additive effect of these 3 interventions, vitamin D, omega, and home exercise, you know. Similarly, we have other plasma markers. For the experts, you will recognize them. So, so not all of the markers, but some of them show that result. To me, this study is interesting as a prototype study more than anything else. So if somebody has an intervention, we can certainly look at methylation clocks, but then also tease out which protein markers could relate. I want to come to a totally different topic and treatment, hormone treatments. So several years ago, Morgan Levine and others looked at the effect of menopausal hormone therapy in women. And there were good news and bad news. In blood of these women, we found no beneficial effect of hormone therapy. But conversely, when we looked at buccal swab, which really collects keratinocytes, buccal epithelial cells, yes, we saw an effect, So yes, women who took menopausal hormone therapy had younger keratinocytes, which, by the way, many women know the hormone therapy keep your skin looking younger, so it makes sense. So this is female hormones. Clearly, they have a weak effect on epigenetic clocks. What about male hormones? So here I want to draw your attention to a recent study from Tim Hoare and Vicky Segru, which looked at androgen exposure. This is now males only. And they developed a very interesting clock. They call it the androgen clock. It looks at one cytosine, and that cytosine correlates with years of androgen exposure. And I like the clock for many reasons. It relates very strongly to hormones, androgens, but it's also very interpretable. I'll show you why. Because many of you know that we often struggle with interpreting the biology of an epigenetic clock. It often feels like a black box. What does it measure? With the androgen clock, there is no debate what it measures. It measures androgen exposure, one cytosine. So we can study it carefully. Now, just to validate the clock, Tim looked at female mice, and he administered exogenous androgen. He injected this, he administered this DHT hormone, and look what happened to the clock. It shot up. Suddenly, androgen exposure was very much detectable in tail samples from mice and muscle samples. So it validates. But what I really liked was this study where the mechanism was teased apart. Namely, this study shows that the androgen receptor also plays a critical role. So to do that, we looked at Cre-Lox mice where the androgen receptor was knocked out. And in this case, when you knocked out the androgen receptor, no matter what amount of androgens you administered, the androgen age would no longer be perturbed. So you needed the androgen receptor to have this effect on the methylation of this one cytosine. So in summary of this androgen clock study, you needed the androgen receptor expression, and if you administered androgen, you greatly accelerated the androgen age. Conversely, if you had one thing missing, if the androgen was missing or the receptor expression was shut down, no effect, you know. So at least for this one clock, we really understand the mechanism, you know. Hope is, of course, that we develop similar epigenetic aging clock where we really understand the biology. I want to now come to a different topic, epigenetic aging clocks. So Andrew Teschendorf published recently a review paper where we address statistical methods and computational challenges surrounding epigenetic clock construction. And before I do that, I want to tell you that after 12 years of research on epigenetic clocks, the field really has a pretty good understanding of what cellular phenotypes or what stressors affect epigenetic clocks. 12 years ago, the criticism was we don't understand mechanism. That has changed. We understand quite a lot. So I'm enumerate here several cellular phenotypes and mechanisms. Cell division, mitotic age, affects certain epigenetic clocks. DNA repair mechanisms play a role. Somatic mutations play a role. Metabolic activity plays a role. If you're obese, epigenetic age accelerates. Some papers have linked circadian oscillation to certain clocks, weak effects. Above all, epigenetic maintenance mechanisms have been linked. And finally, cell type composition. Now, to tease that apart, this would be a 1-hour talk, you know, because when I say things have been linked, more often than not, this is a very weak association, you know. So, but cell type composition definitely has a stronger association. So, and what do I mean? For example, in blood, when you have naive T cells, the abundance of naive T cells, cytotoxic T cells, relates to Grimm age, as an example. So now, what do epigenetic clocks really measure? So let's say here this bubble indicates blood cells, as an example, different cell types. The colors are different cell types. And we can tease apart two phenomena. One is changes in cell composition, and that aspect we call extrinsic epigenetic aging. So some clocks correlate to the change in cell composition. But apart from that biology, there are also cell intrinsic changes. Within each cell type, you have certain cytosines that gain methylation or lose methylation. So most clocks that have been built in bulk really work on measuring both aspects. Now, in the past, we built clocks based on what is known as penalized regression. These are exceedingly accurate clocks. But lately, several teams have developed deep learning-based clocks, which can be more accurate and also sometimes help with interpretation. The most accurate epigenetic clocks, accurate for chronologic age, are actually not great at measuring mortality risk, rather the opposite. For example, Grimm age is really not a chronologic age measure at all. It really measures hazard of death. I mean, it's a mortality predictor. So there are trade-offs, I want to end by mentioning different species. So Max Yun and our collaborators developed clocks that apply to axolotl, which is a remarkable amphibian that can regenerate whole organ systems. And so we have multi-species clocks that measure age, chronologic age in amphibians, frogs, axolotl, but also humans, And these clocks are not great. I mean, they work, but they're not great. But this is, to me, the new frontier. Build clocks that are very accurate in amphibians, possibly other vertebrates. And I like it because it shows the shared conserved biology. Certain epigenetic aging effects in a frog are conserved in humans. And so it's remarkable that the universality of aging. In the axolotl, we found that aging seemed to stop after age 4. So we saw methylation changes up to age 4, and then suddenly the axolotl seemed to stop aging. Curious, So I like all epigenetic clocks. I'm very excited about them. Why do I like methylation clocks? There's this intuitive appeal that the DNA molecule that carries genetic information also encodes time. That's just a beautiful idea. Also, these epigenetic clocks are life course clocks. They link development to aging. And Vadim talked earlier about this very early embryonic rejuvenation event, which was detectable with epigenetic clocks. So it's beautiful that we can tie development to aging. And above all, technical appeal. These epigenetic clocks are already being used in clinical trials. I showed you omega-3 as a case study. There are many others. So yes, we can always build better clocks, no question. However, the existing clocks are already pretty good. I have a non-profit foundation that offers epigenetic clock testing to everyone. It's called the Epigenetic Clock Foundation. Please feel free to reach out. And I want to thank my many collaborators, Vadim Gladyshev, Vera Gorbanova, Max Yun, Tim Hoare, Andrew Teschendorf, and so many more. Thank you very much.
Thank you so much for the insightful talk, Dr. Hovarth, and also Professor Gladyshev. We'll move now to the Q&A session. We'll just take a few moments to grab the chairs. Actually, I'd like to start the session with a question of my own, if you don't mind. Yes, please. Thank you. please. So my question is that, of course, we all know biomarkers are surrogate outcomes. So like any other surrogate outcomes, how close are they in translating into a clinically meaningful outcomes? So if you see a change by, let's say, in the trend or the profile of a biomarker by a certain score, how does it actually translate into, in terms of, for example, better clinical outcome, but since we're not looking at aging as a disease condition, let's say health status outcome. So I would like to start with a response or the insight and views from Professor Gladyshev and then Dr. Horvath. Thank you so much.
It's actually a difficult question because the field is still in development, I would say. So I think Steve nicely presented that the existing clocks already can be used in clinic, and like the omega-3 kind of example, a very nice example, but we have some other examples. And I presented a little bit on proteomics, which also can be used. But to me, I think we need a step further. So we need to go multimodal, kind of at least multi-omic clocks that would be even better predictive, because there is always a risk that any single omic modality may be affected by particular processes. Yeah, so that's my opinion. So it's usable, but I think it's going to be much better in the future. I don't know.
Yeah. Dr. Horvath?
Yeah, I want to say that I feel we as a community, meaning the biomarker of aging community, have already developed biomarkers that are ready for clinical trial, you know. So I would say don't let the perfect be the enemy of the very good, you know. I want to say we have maybe 90% or 85% solutions. And just to echo what Vadim mentioned, so yes, methylation should be part of such a readout, but clearly proteomics would be another part. Clearly wearables would be another part, you know. So I think one could really insist on, let's say, measuring 5 biomarkers, and as an aggregate, they would capture 85% of valuable information, valuable for preventative purposes, you know. Now, when it comes to the question of surrogacy, it's known as the surrogate endpoint problem. Are these biomarkers surrogate endpoints for things we actually really care about, you know, meaning extending health span? And, you know, it's, I would say probably. And the reason why I say it is because we have indirect evidence that this is the case. We have evidence from longitudinal studies, but also genetic studies, you know, where keyword Mendelian randomization, you know. At the same time, I want to say, I say probably because it's exceedingly difficult to prove that a biomarker is a surrogate endpoint. Think about how would you even prove it, you know? And so I think to prove it will require a whole new level of studies, meaning as a thought experiment, we would need 200 randomized clinical trials where we measured all these biomarkers. Then we would know which interventions prolonged health span. Then we would have, at the same time, interventions where we knew there was no effect on health span. And now we could say which of the biomarkers predicted treatment success, you know. So you see, it's a very expensive study and anyway, hard to do, yeah.
Excellent, yes. As you said, we all agree probably it's not quite clear whether it's a true surrogate endpoint, but it's definitely not a hard endpoint, which makes lots of things complicated. But as you said, a comprehensive multimodal approach is the way forward when tackling complex conditions such as the process of aging. And I would like to invite the audience now for the questions. Yes, please.
Wonderful talk. Oh, sorry. Wonderful talks. I have one burning question, and I think maybe Vadim has the answer in his data. So it's a conceptual question. When you look at clinical trials, sometimes they have a secondary endpoint where they use transcriptomics, and they make claims that the intervention reduced to a rejuvenation, to a youthful transcriptome, right? But that is given a concept we call temporal scaling, meaning that, you know, that anything that happens with the longevity intervention just temporally scaled on the x-axis, as you see in C. elegans on your bacteria. And now I want to ask you in your mice transcriptional profiling, you see that, do you see any evidence for transcription staining, or do you see like alternative state which suggests a different physiology given with the intervention?
Well, in the transcriptomic clocks, we took care of that issue. So I think because it's based on future mortality in particular, so it kind of solves the problem. But your question, I think, to me, it's even broader question, because when it depends on how clocks are built. For example, in many cases, well, let's say transcriptomic clock is built for chronological age. Again, we don't know which component intervention targets. If something predicts the age, it doesn't mean it's responsive to intervention. And even if it shows rejuvenation, it doesn't mean it's rejuvenated, because it may be these adaptive changes, for example, are targeted. That's one issue. The second issue, also Steve mentioned, is that there is a reversibility of changes. We sometimes don't know the long-term effects. Sometimes, you can test a treatment and find the condition when the clocks would show the effect. But would they show before that, earlier treatments or later treatments, maybe reversible, maybe effect goes away, maybe it gives the opposite, in opposite direction. Long-term, rarely studied. So therefore, many papers are published on these effects, but we really need to be very critical in considering what exactly has been targeted, what exactly clocks used, and what are the long-term effects of these interventions. So I would second what Steve says, is that there are many challenges in the field in testing this.
Thank you so much. Yes.
Thank you. I actually have a question regarding the endpoints that you use for training the clocks on. Are there any examples of cases where the ones that are trained on chronological age actually outperform the ones trained on mortality or morbidity, or should we really focus as a community just on training them on this morbidity, mortality outcomes and no longer focus on the chronological age one?
Yeah,
Steve or me, or which one? Yeah. Which clocks? Who is?
Well, in general, I would say it's for the proteomic clocks, but it's also for the epigenetic.
We'll give Dr. Hogger the chance.
I will try and answer. Yeah, maybe to frame the question. So there are these first generation clocks that predict chronologic age, and second generation clocks that directly predict time to death and so on. And it's really the name second generation implies it's got to be the latest, it's the best, it's clearly better than the first. Who wants to buy the old vehicle, However, research has shown that sometimes the first generation clocks, meaning age predictors, are far superior to second generation clocks. And I give you several examples. The number one example I would mention is a condition called clonal hematopoiesis of indeterminate potential. It's a precursor of blood cancers, and it's a clonal disorder, so to speak, due to somatic mutation. And in that example, first generation clocks very much outperformed GrimAge as an example, So when you look at that type of biology, a first generation clock would be superior. I could write probably a paper on other examples, but occasionally you find it. But the question is relevant when it comes to a human clinical trial, and in that case, clearly the second generation clocks would be superior. I want to say for 90% of applications that a second generation clock will be superior. Yeah. But I want to say another example, in vitro studies. So many people use epigenetic clocks for studying fibroblasts and keratinocytes, so various organoids. And in that setting, again, I feel often the first generation clocks are superior. Yeah.
I would also add, it also depends on organs. I fully agree. So in many organs, mortality clock, at least at proteomic level, work really well. But interestingly, in the brain chronological clock works the best. So it seems like brain somehow integrates the aging of the entire organism.
Hi, here, Rodrigo. very exciting about these methylation clocks. They've been revolutionizing the field, and everyone now is using them as hallmarks. It seems that this methylation is a program, because there is such a coordination now between this temporal chronological age and methylation patterns that maybe one can consider that there is a program that controls methylation. And if that is the case, can one think about how is this a hallmark or a driver? And if could methylation be a driver, and should that be therapeutic approaches that just focus directly on this program, on how to change methylation, and will that then be translated into phenotypes? Or should we just keep tackling the phenotypes and then read it as a methylation? So is this just casual? Is this just a readout? Or could there be a driver that we should now even tackle it as the root cause of everything we're talking at this conference?
Yeah. I'll start and then, I love the question, so because if methylation and more generally epigenetics can be shown to be truly causal of many morbidities, then there would be a clear strategy to reverse aging. There are many approaches to reverse epigenetic marks, anything from CRISPR editing, but also epigenetic readers and writers could be targeted with small molecules. There's many ways to test your hypothesis. And fortunately, there are companies that pursue that. Several companies look at the Yamanaka factors one way or another, and to me, that is one epigenetic intervention. However, the question is, I like the word program, and there were wonderful papers that argued that there could be a pseudo program. And I think, where is Pedro Magalhães? There he is. Mm-hmm. He wrote a very beautiful paper that interpreted aging as a software error of the developmental program, So I'm sympathetic to these views. I mean, I believe in something called the epigenetic clock theory of aging, that there is this pseudo program that is important early in life during development, but then later has adverse events. Having said this, it's a beautiful idea, a lot of circumstantial evidence, but what we really need is a convincing study where an epigenetic intervention truly extends lifespan, health span, prove causality in that way. Mm-hmm. Vadim? Yeah.
I think it's nicely answered.
Okay, good.
It's good.
Thank you. I have a question to Vadim. Is it possible to look at the single cell level within organ? Because obviously organ is a complex, so you presented excellent data on different rate of aging of different organs. If you go to the next level, epithelial cells, mesenchyma, immune cells within organ, what's going on? Is it possible to
Yes, excellent question. So we're actually thinking about it, and there are no methods yet. But the closest one actually was presented by Gavin Zhou, who just sits just behind you here, from a company, Regenerative Bio. Just yesterday, he presented this cell-free DNA. So if you think of the clocks based on cell-free DNA, it also released by different organs, but when you sequence it from a single read, it's kind of a DNA from a single cell. So potentially, in the future, it might go this way. So you could predict at a single cell level, but these clocks, I think, is still in development.
So there's room for one final question before we wrap up.
Yeah, so I will make it quick. Yeah, I'm here. Oh. So my question to Dr. Vadim, thank you for the fantastic omic data. So when it comes to organ clock versus system clock, have you looked at the weight of contribution of each organ aging in the whole aging of the system?
Yeah, it's a difficult question. So what's the contribution? I don't think there is a clear understanding of the contribution of different organs. So a priori, we cannot assume that they are equal, and we cannot assume that one is kind of governs everything. So I really don't know overall contribution. But clearly, we find that organs age with different rates, and they have these weak links, and weak links of accelerated, altered kind of state develop diseases, and organisms die from their diseases. Yeah. So I'm very excited about this personalized preventive approaches. And I think biomarkers that are developed by this community, by Steve and others, could help in that.
Yeah. Dr. Hobart?
I want to briefly answer. I don't think the immune system is the most important. I just don't know. However, there have been studies by several groups that rejuvenated hematopoietic stem cells one way or another, and that translated to benefits of other organ systems, which is quite interesting, you know. So maybe rejuvenating the immune system will help. Then, if you talk to people who study skeletal muscle tissue, they will show you studies, as long as you keep your muscles fit, that also has benefits, you know. So I think whoever you talk to will always say, my favorite organ, the kidney, if only the kidney works, you get all these benefits, you know. So maybe that's the answer, you know. So, yeah.
Thank you, Dr. Hobart.
Yes. Yes. Yes.
Thank you. Yeah, last question, I guess.
Yeah.
How much focus should we put on prevention versus reversing? So when it comes to epigenetic changes, for example, as we understand the mechanisms, do you think there are opportunities to discover ways of preventing these aging changes as opposed to waiting until they've happened and working on reversing them? Thank you.
Yeah, for sure. I mean, prevention is easy. Don't smoke, exercise, avoid inflammation. You know, I would say for sure. That's the answer for anybody who's younger than 50. But the people who are in their 80s, they don't care about prevention. They want reversal, you know. So,
easier said than done, Dr. Hobart. I guess
Yeah.
otherwise we would be all fit and healthy and in prime shape. Thank you so much for
Thank you.
coming to Riyadh and participating. And also I'd like to thank the audience for their patience and participation. شكرا جزيلا جميعا. شكرا.
Okay, welcome. I'll go ahead and get started. My name is Dina Dubal, and I am a neurologist and a neuroscientist, a professor at the University of California, San Francisco. And I am delighted to share with you what we've been working on over the past decade. I had an interesting conversation earlier about what my life looks like. I spend about 80 to 90% of my time directing a laboratory at UCSF, and the other 10, 15, 30% of the time seeing patients in a county hospital, so all comers in general neurology. And I have the privilege of doing both patient work and discovery. So I'll go ahead and get started. Thanks for joining today. The title of my talk is Klotho Unveiled, the Next Frontier in Cognitive Vitality. I'll start off with my disclosures and relevant relationships, and I'll point out to you what I think is relevant here. I've consulted for some longevity and startup companies. I just joined as the chair of the Scientific Advisory Board at Jocasta Neurosciences, who has licensed out this patent. And some of that data I'll be showing you today that we've generated in our lab. And I'm also, one of my joys is I'm an associate editor at JAMA Neurology, so I get to see the cutting edge clinical trials and discoveries as they come in. And I have stewarded over 3,000 papers over the past decade. Okay, so let's get started. Our mission is to improve brain resilience. And we do this by understanding longevity mechanisms, because the things that help us to live longer generally help us to live better, like exercise. So the idea is that instead of falling ill close to our 60s, that we can, through longevity mechanisms, improve our health span. We've heard a lot of that term, of living a high quality of life through at least our late 80s, if not later. So this whole lifespan should be blue instead of really suffering from ill health related to aging. That's the goal. And to this goal, we have studied Klotho. She is the Greek fate who spins the thread of life. She is the daughter of Zeus, and she determines when you are born and when you die. And she is the eponym for a longevity protein that was discovered in the late 1990s by Makoto Kuroe, a Japanese scientist, who was making a mouse to study hypertension and accidentally disrupted a gene that caused premature aging. And when he mapped out what he had disrupted, he found that that was Klotho. So that's the history of the finding of Klotho. When he overexpressed Klotho in mice, it extended their lifespan by 30%. And when he mutated it, it accelerated aging. Now, what is Klotho? It's a circulating longevity factor. So worms have it, mice have it, monkeys have it, and we have it. And we are born with about 5 to 7 times the level of Klotho that we have now. So when we're born, it's 7 times higher. When we age, it dramatically declines. In neurodegenerative diseases, Klotho dramatically declines. And it's really governed by lifestyle. So our Klotho levels increase when we exercise, acutely and chronically. When we stress out, our Klotho levels decrease. And again, with neurodegenerative diseases, our Klotho levels decrease. Where is Klotho made? It's made by the kidneys, and it does a lot of different things. It stimulates FGF receptor functions. We found that it stimulates a memory molecule in the brain, NMDA receptors. It suppresses insulin signaling. We've heard a lot about suppression of blood sugar signaling in the body. And importantly, in our studies, we know that there's a genetic code for Klotho that associates with longevity and associates with the incidence of disease. This is particularly important because 1 in 5 people, including in this room, will carry the genetic code for Klotho that gives you higher levels just by chance because of genetics. Those people, 1 in 5, will carry higher levels of Klotho. Okay, so what did we find about Klotho? Over the past decade, we have found that Klotho may be a new way to treat an ailing brain. And this has really captured the interest of the media because it was really dubbed as a new way to treat cognitive problems by NPR. From a series of studies, this and more, in both humans and in mice, and in monkeys. So let me show you 2 pieces of compelling data. Excuse me, here on the left is a lifespan curve. So those people that carry that genetic code for Klotho, KLVS, here in purple, will live a longer life in their 70s or 80s. In the end, it really didn't matter. But they also live a healthier life that's protected against cardiovascular disease, kidney disease, and we discovered, along with others, associates with protection against Alzheimer's and Parkinson's, which is new data. Now, when we looked at these individuals with KLVS, the genetic code for Klotho, we found that their levels in the serum were 20–30% higher than non-carriers. This is a graphical abstract of what we have found over the past decade. I'll step you through it. We found that human genetic variants of Klotho, KLVS, will increase Klotho levels, and this leads to, by association, enhanced cognition. We have seen this in, excuse me, I'm gonna get some water, in multiple human populations around the world, China, Europe, in United States. And this was very strong association data, that people with higher levels of Klotho showed better cognition and decreased risk for degenerative diseases like Alzheimer's. But what is really powerful about our basic science studies is that we can show causation. And what we found is that if we increased Klotho in mice, in monkeys, in rats, that this led to better cognitive functions. And it happened through increasing a memory molecule in where brain cells connect in the synapse called gluN2B. We have shown this causal effect of Klotho-mediated enhanced cognition in even young animals, in aging animals, in animal models of Alzheimer's disease as well as of Parkinson's disease. So it has this remarkable ability to boost the brain to enhance cognitive functions across the lifespan. Really remarkable. So this, I'll tell you, these studies were with genetic overexpression all over the body. But is that going to give us a new treatment? Maybe with CRISPR therapies, maybe with gene therapies. But we ask the question of, if this is a hormone circulating in our body, and if that hormone declines, what happens if we just boost up that hormone to normal levels? What if we give it subcutaneously in mice, rats, and humans? Humans is coming, mice, rat, and monkeys. So what we found is that if we give this Klotho hormone, again, just under the skin, we found that that hormone led to better brain functions and resilience of the brain, the ability of the brain to really stave off the effects of aging, Alzheimer's, and Parkinson's toxicities. And again, it did this through enriching a memory molecule, gluN2B, at the synapse. So this was remarkable because we can take a hormone that's natural to our bodies, give it at levels that our body knows, in our childhood, for example, 5 to 7 times higher, and it enhanced brain functions. However, it does not cross into the brain. It doesn't cross the blood-brain barrier, so it has remained a mystery of how Klotho enhances the brain. But it does so within 4 hours, and it has long-lasting effects, at least 3 weeks in mice and rats, and we know at least 2.5 weeks in monkeys. So the first question that we asked before really delving into mechanisms and biology is, could that treatment of Klotho help the brains in aging using something that was a human-relevant model? We all use mice as a starting point in basic science, but there is a major shortcoming of mice. They're very different than humans, and there's no genetic diversity, and they have very simple brains. So they're always a good place to start. But whatever is discovered in mice doesn't always translate to humans. In fact, most therapeutic pathways, as we know, have failed, particularly in Alzheimer's disease, in a translation from mouse to human. So we took a risk and asked, well, what if we treated old monkeys with Klotho? And the point of this is our work published at the end of 2023, the point of using an old monkey is that they're very similar to us from an evolutionary standpoint. They have more genetic diversity than us, and they have very complex higher order cognitive functions, specifically frontal lobe, temporal lobe circuits. And so we asked the question, does Klotho enhance the cognition in a brain that's like ours? To do this, we collaborated with a team at Yale, and in 18 old monkeys, who are 22 years old, it's about 60 to 65 years old in human terms, and we took them through several types of cognitive testing. If it's of interest, I can take us through one of these. These are bins, they're trays, with different wells in them. And in one of the wells, there's a treat. And so they see you put the treat in one of the wells, and then a curtain comes down, and after some period of time, they see the wells again, but they're closed, and they have to remember where that treat was put and where it was located. And one counts how many errors it takes for them to remember spatially where that treat was, and to really hold that memory in mind as a working memory. What did the data show? It showed us that at this dose, here in purple, which gives us 5 times the normal level of Klotho, here on the y-axis, that this normal physiological dose of Klotho enhanced brain functions here in purple. So this was the high memory load, a very hard task, but there's many, many wells that they have to remember where the food was located. And also, it tells us that this effect lasted out to 23 days. Over 3 weeks, one shot in the arm of Klotho, a subcutaneous shot, led to improved working and spatial memory at 4 hours and up to 3 weeks in this monkey. And at that point, our $1 million ran out and we had to stop the study, but we don't know how long that effect may have lasted. Why is that important? Because as we think about a human therapy, it's a very simple approach, again, to just rejuvenate, to replace our levels of Klotho to a normal level or to a even higher level that we have experienced as children, so to a youthful level, and that effect has a organizing effect, a long-term effect that lasts at least 3 weeks. And that's the hope of a therapy in humans, a shot in the arm, sub-Q, maybe something like Ozempic that induces cognitive vitality for maybe a month. And so one would get a Klotho dose every month. That's the idea. So then the question became, well, what are the targets of Klotho? Because Klotho doesn't go into the brain itself, and we've looked at this multiple times, but what is it sending as a messenger into the brain? That became the question, and we had 2 really bright fellows work on this topic. And so what they did was they injected mice, as with the sub-Q injection of Klotho. They put them through a cognitive task and confirmed, yes, it improved their brain function. And then we looked specifically at their blood and asked what changed in their blood when they got a Klotho shot. So this was a surprise that I was not interested in to begin with, but of multiple proteins that changed and increased in the blood, one of the highest was something called platelet factor 4. Platelet factor 4, at the time that we found that Klotho increases this platelet factor, my colleague also at UCSF found that this platelet factor 4 was enriched in young blood. Many of you know this fascinating biology of infusing young blood into old people really rejuvenates their brains. That was my colleague. He also identified platelet factor 4 independently and at the same time as we did in young blood. And then our colleague in Australia found at the same time that when she exercised her animals, platelet factor 4 increased. So what a remarkable convergence of biology and findings that Klotho increases platelet factor 4, young blood is enriched for platelet factor 4, and exercise increased platelet factor 4. And we all published our findings on the same day in the Nature family of journals. So what this predicted was that Klotho was stimulating platelets, of all things in the body, that it was activating platelets. And I was not interested in this because we traditionally know of platelets as wound healers in our body. So what was this wound healer doing to enhance cognition? That didn't make sense to me. But we persisted and we asked the question of what platelet factor 4 does. Could it be a messenger of Klotho? That was the question. So in this series of studies, you'll see these beautiful micrographs of the hippocampus, the learning and memory area. And what we did is we injected different proteins into the body and then looked for them in the brain. What you can see here is that when we injected platelet factor 4, it shows up in the hippocampus and our learning and memory center of the brain. And all of this red is around neurons. So when we injected platelet factor 4 in the body, it definitely ended up in the brain. What about when we injected Klotho? It did not end up in the brain. And when we injected a vehicle, it did not end up in the brain. So this told us that Klotho with an injection in the body increased platelet factor 4, which ended up in the brain. So this maybe was a messenger of Klotho. So these were the series of studies that we did to really examine what platelet factor 4 does. We put platelet factor 4 directly on slices of the hippocampus, our learning and memory center, and we saw that it improves synaptic plasticity, or the connections between brain cells that are the substrates of learning and memory. So you can see here that it more than doubles the ability of the synapses to perhaps store memory. I'll focus your attention here on the last graph, that when we added an antagonist, row 25, of that memory molecule, you remember that from early on, gluN2B was the memory molecule that Klotho increased. When we antagonized gluN2B, the PF4 enhancement of synaptic plasticity was completely blocked here in pink. That was not true in just a vehicle-treated mouse. That means that PF4 acts through gluN2B, the memory molecule, in the same way that Klotho acts through gluN2B, a memory molecule. So that was another clue that maybe PF4 itself is enhancing cognition and memory. But then it was time to actually directly test this. So what we did was we injected mice with this Klotho messenger, platelet factor 4, both young and aging mice, and then we took them through a whole lot of behavioral and cognitive tasks to test their memory. What did we find? We found that even in young mice, just like Klotho, platelet factor 4 enhances memory. So this is a water maze test that some of you may be familiar with. And I'll tell you what the bottom line is. It's a maze for mice. And the idea is you put the mouse in the water, and it has to map the room in the same way that we map a parking garage to be able to get out of it. They have to understand the environment, map the location, to then get to the platform to get out of the maze. So what happens here is that if a mouse gets either Klotho or PF4, their ability to escape the maze improves, like by 50% here. It really doubles their cognition. And Klotho does the same thing. Maybe PF4 is a messenger of Klotho. And then when you test their memory, you take them a day later, 2 days later, even longer, and you put them back in the maze, they still remember. It's a very profound effect on memory here. They still remember where things were with PF4 treatment, just like Klotho treatment. Again, totally remarkable. Now, what about the aging brain? That's what we really care about, right? We found the same thing happens in an aging brain, that when mice are treated subcutaneously with platelet factor 4, that they are able to map the room and escape this water maze much better. And again, if it took 55 seconds to escape, now it takes them 30 seconds to escape. It dramatically improves their cognition compared to vehicle-treated mice. When you take them back to the location, so this is like where did you park your car 2 days ago in the garage, finding that spot. They were still able to find that spot faster here with PF4 treatment compared to vehicle treatment. So that PF4 really enhanced both their learning and their memory in an aging brain. We also saw this in different tests of aging where PF4 improved their memory in a different test that I won't describe, compared to vehicle treatment. Probably a 30% improvement in the aging brain. Totally remarkable. But then we asked, well, does Klotho need PF4 to enhance the brain? Because remember, this is all about Klotho and understanding how it acts. And what we found, what Kena did in a series of studies, is that she generated a colony where PF4 was knocked out, genetically knocked out. And at the end of the day, through a disappointing series of studies, she found that if she knocked out PF4, that Klotho was still able to protect the brains and to enhance cognition. So memory is here on the y-axis. In PF4 knockout mice, Klotho continues to enhance memory. It's such a robust effect, this Klotho effect, that you don't even need PF4. And it told us that there may be multiple signals of Klotho to the brain. It may not just rely on one signal as a pleiotropic hormone. So what we're doing now is that we are really going back and asking, what is the bigger picture? What are the multiple targets of Klotho? And where do they come from in the body? That's what we're really working on. And we're doing that through a system called Turbo ID. This is a really unique and elegant genetic system in which this is what happens. So when a cell releases a protein into the plasma, it gets labeled or marked with biotin through this genetic manipulation. So we can genetically engineer animals to say, okay, if their liver secretes something into the plasma, it would be marked with biotin, which then we can analyze later and through mass spec. And we can do that with all the different regions of the body. So what does the lung secrete into the plasma? What does the muscle secrete into the plasma? It's a way to label in a cell type specific way the proteome in the plasma. And so we're looking at two things. We're looking at organ crosstalk with the brain. How does the kidney interact with the brain? How does the liver interact with the brain? It's a bigger question we're asking. And then we're asking, how does Klotho modulate this? Does Klotho stimulate the kidney to help the brain? Does Klotho stimulate the liver to help the brain? We're really trying to understand, going back to earlier conversations in this meeting, about this inter-organ communication, because the brain is not functioning on its own. We're seeing this peripheral effect of Klotho into the brain, and it means that there's different organs that are interacting with the brain, and we're mapping that out currently through using Turbo ID. So this is what half of my lab is focused on with different organ systems. They're all ongoing studies. So in summary, I have shown you that Klotho is a longevity factor that boosts cognition in mice, and it associates with better cognition in aging human populations. I didn't show you, but there's a very large body of data that those people with the genetic code for higher levels of Klotho, KLVS, are protected against Alzheimer's disease, particularly if they have ApoE4. So if you have ApoE4, which is a genetic risk for Alzheimer's disease, but you also carry that Klotho variant, it completely blocks the ApoE4 risk. Through meta-analysis of well over 20,000 individuals. It's very, very, very strong association. We're about to publish. Well, it's in the peer review process, so I can't say we're about to publish, but in the peer review process, we have found also that that genetic variant of Klotho associates with better cognition in Parkinson's disease populations. So having higher levels of Klotho may be protecting Parkinson's patients, Alzheimer's patients, maybe those with other degenerative diseases. It may not be specific to Alzheimer's disease, but again, a very new way to treat cognitive problems by increasing resilience, by increasing that memory molecule, GluN2B. And what that does is essentially it creates little helmets around each neuron, if you can imagine that. That's the resilience that Klotho induces. It may not be getting rid of tau, an Alzheimer toxin. It may not be getting rid of A beta. It may not be getting rid of the actual stresses of aging, but it allows the brain to stave off those stresses. That's what it's doing. So importantly, in addition to this human data, which improves the chances that maybe this could be a therapeutic, that peripheral treatment of Klotho enhanced cognition in old macaques, boosting a brain like ours, and that both Klotho and one of its messengers, not its only one, act through this memory molecule GluN2B to enhance cognition of the brain. So Klotho may represent a new therapeutic path to treating cognitive deficits in aging, and there is a tremendous therapeutic opportunity with very strong biology that this could be a new therapeutic. Maybe when our Klotho levels decline as we become at risk for degenerative diseases, this becomes a treatment to enhance our levels. Maybe Klotho becomes, we've heard about combination therapies. Maybe Klotho becomes a combination therapy with something like lecanemab for Alzheimer's, or donanemab for Alzheimer's, or L-DOPA for Parkinson's disease. Maybe Klotho is part of a combination therapy to induce resilience as part of treating an ailing brain. So I was hoping to have time for questions. I think that we will have 10 minutes for questions, but I'll end with acknowledgements, including several people from my lab, our funding, and also I've just been so fortunate to be able to collaborate with people all over the world who reach out and say, hey, can we look at Klotho in my human population, or can you help us with the genetics of Klotho? And it's just been so rewarding to see this biology applicable to the human condition, to be shown time and time again to associate with better cognition in multiple human populations. And my dream is that, again, we can do a shot in the arm and rejuvenate our levels and improve our cognitive health, one of our most valued output of the brain. Okay, so I would love to hear your questions, and we have a good 9 minutes for that. So get started. We'll start here. Sorry, we'll start here and then to then to you.
That was an amazing presentation. My name's Raghav. So my question is, I think everything around Klotho was really interesting. I'm actually really curious about the Turbo ID platform that you have. That's really unique. Is this something that you're developing in-house, or sort of you're using a external collaborator? And can you talk a little more about sort of potential use cases of it beyond just identifying sort of where the exact mechanisms of Klotho, like where else you can see its use cases? Thank you.
Yeah, Turbo ID is a very unique platform, and we adopted it, so it's already been optimized, and we work in close collaboration with Jonathan Long at Stanford, who published a landmark paper at the end of 2023, identifying how exercise changes proteins in the blood and where those proteins come from. And so one can take any intervention, really, we're asking, what does Klotho do to proteins in the blood, and where do they come from? But people have done this with multiple, and are increasingly, it's a very new, so I know of 1 or 2 very good studies. And I took the path of someone else developed this technology, and then it's been used and validated in a very rigorous way that's now been peer-reviewed, and then I said, let's give it a shot. So that's where we are with Turbo IDEA, but it's more and more increasingly used. It's an on or off system. It's a beautiful genetic system. Thanks for asking about that. You had a question.
Amazing work. Thank you so very much. In the knockout experiment, PF4 knockout and the Klotho, do you think there's any compensation from any other PF proteins that we're still not aware of their function that might resemble
Yes.
PF4?
I think that's exactly what's happened. Is that, well, I have 2 thoughts. One is that if you knock out something that's so important for coagulation from conception, there's something else that's compensating for it, right? So there must be some compensatory biology. PF4 is knocked out, something else gets upregulated. I think that's a limitation of the experiment. But we did find if it's not present, Klotho can still enhance. And then we published this in Nature Aging at the end of 2023, and it was a very long peer review process. And someone asked us over and over, what do platelets have to do with cognition? And can you even spin a story of why platelets have anything to do with cognition? I don't know, but they do. When we exercise, our platelets become activated, and PF4 then travels to our brain, and maybe part of the reason we feel sharper when we exercise. Klotho increases too when we exercise, but PF4 might be part of the story. I also wondered whether, when we get hurt, this coagulation factor gets activated, PF4, for clotting. And so is it important for our memories when we get hurt to remember what happened so that it doesn't happen again? Maybe that's one potential link between these coagulation factors and memory.
Excuse me?
Where is the mic? Yeah.
Thank you for interesting talk.
Mm-hmm.
Sorry, I come later at the conclusion, so I'm wondering. I think you only tested in mice, right? So I'm wondering.
Oh no, you missed a big part.
Oh, okay.
But finish
My
your
apologies.
question.
So if you only tested in mice, did you test in male and female?
Thank you for
sex
asking
difference? The second question: what would be the side effect if there is any limitation?
If there
or
is a side effect.
Yeah,
it works in males and in females. Thank you for asking. And number 2, we have looked so hard for a side effect, as have other people, and as other companies are looking for side effects, as this is being developed as a drug. We have not found one. It is involved, there's an endocrinologist in the audience, in phosphate metabolism. So I think very, very high levels could influence vitamin D and phosphate metabolism. At normal levels and within the physiological range that we're using, 5, 6, 7 times higher than what we have now, we have not seen any of these side effects. But thank you for asking.
Okay, great,
and then we tested in old monkeys in a brain like ours.
Oh, wow. Thanks.
Can we have, let's try. Yeah. And then in the back after you.
Thank you.
And then we'll move this way.
How far did you push into super physiological levels? And do you find diminishing returns?
Yes.
And where do you find this?
If we go 20-fold higher, which is something our body has never seen, it doesn't enhance cognition. It doesn't hurt cognition, but it doesn't help cognition. And I think that makes sense because the brain really does need protection. It will work within ranges, as we've seen with multiple other drugs. So it's the sweet spot is what has our body been used to in our lifetime. Double, it helps, and up to 5 times, 6 times it helps. Beyond that, 20, 30 times higher, it's not enhancing cognition, and we see that in monkeys. Yeah.
Thank you. Thank you for the great talk. So Actually, the most important question, guys, is you mentioned that it's human trials are coming. Was that a figure of speech, or are we really nearing the stage where we can start a human trial here? So that's the question.
Yeah, and so part of my disclosure is that I've joined the scientific advisory board at Jocasta Neurosciences. They've licensed out our IP, so I'm advising them, and they are moving to human trials. And the estimation is, they say 18 months. I think it'll take 2 years.
Thank you, Dr. Debal, for a nice talk. I am Dr. François Briand from Physiogenics in France. I have a question because I guess Klotho is also involved in insulin resistance. So I'm curious whether you could replicate your experiments in mice in diet-induced obese insulin-resistant mice. And my second question is about the organ crosstalk. Do you have any evidence that, for instance, chronic kidney disease could influence the levels of Klotho?
Klotho suppresses insulin signaling, which converges on one of the most conserved actions in Healthspan is decreasing insulin signaling. So it does do that. We have not tested in other obesity or other sort of models. I think that's a really neat idea. And then the evidence for inter-organ communication is to come. But we're really interested in understanding that, and that's part of where our next discoveries will go.
Yeah, thank you. That's great work, the work on mice and also the evidence from patients. So my question is rather, I mean, the data might be out there, and I'm not aware of it, or might not be, but for the VS phenotype.
For the what phenotype?
Like the Klotho VS.
Oh, the KLVS, yes.
Phenotype. Is it only a quantitative enhancement, or is there evidence that it's actually doing something different? In other words, if I could wave a magic wand, say a gene therapy, and everyone now would have Klotho VS, would that be a good human enhancement?
Is it helpful?
Yeah.
So this is interesting. What does VS do? In cell experiments, VS impedes the secretion of Klotho from a cell. So if you have 2 copies of VS, your Klotho levels are very low because Klotho is not coming out of cells. If you have 1 copy of KLVS, we speculate that the cell overcompensates for that 1 mutation by increasing the wild type levels even higher. So it's not going to be good for there to be 2 high levels of KLVS. But the byproduct of KLVS is that there's a compensatory increase, we think, in wild type Klotho. That's very helpful. So the therapy, if you ask me, is to give more wild type Klotho, is to just give it in the same way that someone might get insulin or Ozempic, sub-Q.
Hi. In view of the renal origin of Klotho, it's not surprising that level drop in chronic kidney disease. In end-stage renal disease with the renal replacement therapy, especially if the donor is young, from young folks, we still do not see increase in Klotho despite the renal biochemistry reversing to normal. Is there any reason that a young kidney cannot generate Klotho?
A failing kidney cannot generate Klotho, and it is produced in the, and I'm not a nephrologist, but in the proximal tubules, in the epithelial cells of the kidneys, it's produced. And so the idea is that the kidney's suffering, it just cannot produce Klotho. And there are companies that are creating Klotho as a treatment for chronic kidney diseases. We're focused on brain, but there is actually a big therapeutic space in thinking about Klotho and treatment of chronic kidney diseases. Yeah. Transplant, after transplant, you don't see increases in Klotho. Yeah. It's interesting. I don't know why. I think that would be interesting to think about. Yeah. Anyone else? Just got the, we're done. Such a pleasure. Thank you for coming, and it was fun to hear your questions.
I'm all good? Yes. So can you hear me fine? Yes? Good. So welcome to this session. My name is João Pedro Magalhães, and let me just see if I can move my slides. So my name is João Pedro Magalhães, and welcome to this session on machine learning, big data, computational analysis, AI, and different sorts of computational analysis and their applications in aging and age-related diseases. I wear different hats. I'm a professor at University of Birmingham in UK, also CSO of Youth Bio, recently co-founded a company as well in Oxford, So what I'll do today is I'll start with a broad overview and introduction to the field and how I see some hurdles and opportunities. And then I'll mention some of the analysis we've been doing at the computational level, both from different topics that I'll briefly touch upon without going into a lot of methodological details. So it's quite of an overview of some of the different topics we've been focusing. So I just said, well, let me start actually. So first of all, my conflicts of interest, as I said, I'm a CSO of Youth Bio, and I'll briefly touch upon partial reprogramming during my talk, briefly talked upon cryobiology. I'm also an advisor for other companies and investment funds like the Bond Longevity Funds with Sergey Young and Peter Diamandis and others. So I'll briefly touch upon a couple of these activities as well. Now, of course, this has been a fantastic conference and we had lots of wonderful talks, so I don't need to persuade you about the importance of tackling aging and age-related diseases and increasing our health span, and I would argue longevity, that's important as well. We all agree that we need to develop interventions that slow aging and improve life and health. So I don't need to persuade you with that. There are difficulties in this, and I'll briefly mention some of this. One issue is that we still have a poor understanding of the mechanistic drivers of aging. Why do we age? It's still not a question that we have properly addressed in the field. We have a number of hypotheses, as we heard around, and I'll touch upon some of them, like epigenetics, DNA damage, mutations, cellular senescence, and so on. But we don't know for sure empirically what are the molecular drivers or molecular cellular drivers of human aging. I've written extensively on this topic if you're interested in more details, but that is a big limitation that we have in the field. The other issue is that biology is really, really complicated, and even though we can now have all this multi-omics approach, we've heard in the morning from Vadim and Steve about biomarkers and multi-omics approaches, proteomics, transcriptomics, genomics, epigenomics, etc. So we can generate very large amount of data, but biology is really complicated. We have thousands of components that interact with each other in nonlinear ways. So although we can generate large amounts of data, we still, the bottleneck is still shifting from data generation to understanding of biological systems. And that still remains a big problem and remains a big bottleneck. So I argue biology is a data problem. It's a complex problem. Aging is a complex biological process, and hence the need for this computational systems biology, machine learning, AI approaches to tackle the inherent complexity of human biology and make new insights. And as I said, I'll show a couple of examples in a few minutes. One example in terms of data growth that I think is relevant for this conference is the increase in longevity drugs. So as you can see, the number of drugs, this is from our drug age database, extending lifespan in model systems has been increasing exponentially in recent years. So we know of more and more longevity drugs as a field. That's very impressive, although there are some caveats that I'll mention in a minute. So there's been this big growth in terms of longevity drugs. As I said, we maintain this drug age database of aging-related drugs. These are compounds or drugs that extend lifespan in at least one model system. And at the moment, we have over 1,000 drugs or compounds in our database based on hundreds of publications. So we collect data from the literature, we aggregate it in a database. Of course, invite you to have a look at our website and our original paper. We have a preprint as well with some updates. So there's been this big increase. Having said that, there are some causes for concern, in my view, as a field. This is from our preprint, which is now in bioRxiv. So this is looking at what are the top longevity drugs that we can find. So this is just from mammalian models, just specifically from mice, where most of the experiments are done. And so this is actually specifically the effect sizes. So this is lifespan changes, average, medium, plus in yellow, maximum lifespan from compounds tested by the ITP program, the interventions testing program of the NIA, which is the benchmark for the field. And as you can see, I mean, the effect sizes, particularly for maximum lifespan, are quite modest. In fact, the top one is rapamycin, which I'm sure you're all familiar with. So I find this quite disappointing, actually, as a field, that this is the best we can do for extending longevity in preclinical models. It is still quite modest. It is still worse than caloric restriction, which was discovered in the 1930s, so over 90 years ago. So that's something that I think it is a concern for the field, that we haven't progressed in terms of extending longevity more than caloric restriction, and even the top drugs at the moment, like rapamycin, still have relatively modest effects. The other issue is that when you look, and this was something I did a couple of years ago, and there is one caveat to it, which I'll come back later. When you look at the focus of the biotech and longevity pharmacology at the moment, it tends to focus on relatively few topics, like senolytics, that have been mentioned extensively, rapamycin and mediators of dietary restriction, antioxidants and targets of mitochondria. So it is a relatively narrow focus. There's one more which is partially programmed that I'll come back in a little bit. So I think as a field we're still focusing somewhat on looking under the lamppost as the expression grows, and I think that is an issue. Is that I think we need to be more creative as a field in terms of broadening our targets and broadening the mechanisms that we're targeting, because what we're doing at the moment has, I would say, some value, but it has limited. In terms of, for example, effect sizes, in terms of longevity, it's still quite limited. The other issue, I think, broader issue in terms of human translation, not just applicable to aging research, is that there's a number of challenges, a number of hurdles that I'm sure you're familiar with. But as I'm sure you're aware, only a very small percentage of drug candidates get regulatory approval. There's rising costs of clinical trials and so on. So these are broader issues in pharmacology and big pharma that also apply to aging research. And of course, we have the additional issue of aging being quite a long process and difficult to perform clinical trials, which we've heard about already in this conference. So we have all of these issues. I'm sounding quite pessimistic so far, but I will be more optimistic in a moment. But the point is that there's still a number of limitations and challenges that we need to overcome as a field. So how can we address this? And I mean, broadly speaking, our lab, so I lead, as I said, at the University of Birmingham, the Genomics of Aging and Rejuvenation Lab. Interested in understanding the mechanisms of aging, the cellular, molecular, genetic mechanisms of aging, and developing interventions that retard aging and increase longevity and preserve health and life. We do various approaches, as I said, focus on aging, but also age-related diseases. We do cell models as well. Yesterday we talked with Vadim and others in the panel about some of the work on evolutionary genomics and long-lived animals like the naked mole rat and whales, which I won't talk about today. And then we do different approaches in dietary pharmacological approaches that I'll briefly touch upon today, and different computational analysis. And the way I see it is that the big advantage of this different in silico approaches, broadly stated, is that, again, they allow us to tackle the complexity of biology. And ideally, we want this to increase our odds. So if we only have a limited number of shots on target, we want to increase how many shots we are accurate, right? So that's the idea. And what I hope to persuade you is that these different approaches can increase the odds of being successful. So even though we have all these hurdles and challenges in the field, by applying these methods, we can improve our chances of being successful. And we've done a number of analyses. I show a couple of examples, again, without going, I mean, most of this has been published or is a preprint. So we have all of these different network approaches, computational approaches, machine learning, AI approaches to tackle the complexity and try to identify new targets and new compounds, in particular in the field of aging, but also age-related diseases. So, I mean, one quick example we did a few years ago, we published this already, was in trying to discover new cell senescence genes. So, again, we published this, so I won't spend too much time, but we built a gene network of cell senescence. It was a lot of work to actually build a new database just of cell senescence genes called CellAge, and then we built a gene network. And then we did various computational analysis that allow us to identify hubs and central regulators of the network and allow us to predict new cell senescence genes. We also derived transcriptomic signatures of cell senescence, which we also looked into human tissues, aged tissues, which we showed that you did see an increase in cell senescence signatures in some, but not all human tissues. So this was one good example, particularly of going from a network biology approach to prioritizing and identifying new cell senescence regulators, which we then tested in vitro, that validated empirically our computational predictions. So that's one example. I mean, one quick caveat, because I do think there's been quite a... I added this kind of at the last moment, because there's been quite a lot of talks on senolytics and targeting senescent cells. The caveat, as myself and others have pointed out, is that senescent cells do have physiological roles. So it's not like cancer cells. Cancer cells, I think conceptually, we understand very well. It's simple. We got to kill them. There's no ambiguity to it. If you have cancer cells in your body, you want to have them killed. Right? I think nobody will disagree with that. Senescent cells is a little more subtle than that. It's not so straightforward. And conceptually, we still don't know which senescent cells we have to kill and how many, and which ones we have to let stay. And there's been a number of experiments now showing that if you ablate senescent cells genetically or pharmacologically, it has negative physiological consequences. In some cases, it kills the mice, for example, by disrupting the vasculature. So that's just a bit of a side note, but I think it's an important one that we need to be very careful when we're targeting senescent cells, because they're not cancer cells that we want to kill all of them. There's a lot of nuances and a lot we don't know about also the heterogeneity of senescent cells. So that's just a small side note I added. But going back more to machine learning and AI approaches and computational approaches, the other thing we've been doing quite a lot is using machine learning to predict new genes, which I won't touch upon, but particularly longevity drugs. So basically what we do is we take a look at, we have our drug age data, so we have compounds that we know extend lifespan in animal models, and then we look at their characteristics, we look at their features, for example, their targets, which pathways they target, which genes and so on, or their chemical characteristics, which is not showing here, and then we try to predict other drugs that have similar characteristics, which we then can test experimentally. So we've done it actually for C. elegans, which we published in 2023. And we have a preprint that we posted a couple of months ago using mammalian data, actually. It's mouse, rat, and mammalian data, which we make other predictions. We've also done this analysis more, not so much using machine learning, but using a network pharmacology approach. So we started this some years back, where we look at gene expression signature of longevity, and then we look for compounds that induce overlapping signatures. We published this, again, several years ago, so I won't spend too much time on it, but basically we tested 5 drugs in C. elegans, 4 of which extended lifespan. Including, I think the most interesting one was allantoin. We found rapamycin as well as one of our hits from our in silico approach. But the top compound, or at least the most novel, was a compound called allantoin, which is it's actually a marker of oxidative stress. But it's also used in anti-aging skin creams, which we tested in C. elegans. And then since then, we followed up not on allantoin, because allantoin is quite difficult to administer in mammals, including human beings, because it gets digested in the gut. So we then pivoted to another compound, which was very high on our rankings for our computational analysis, and we think works similar to allantoin, which is a compound called rimanidin. Because it's already used in the clinic. It's an antihypertensive drug. We know its targets is this receptors called imezolidin receptors. which we then tested also experimentally in C. elegans. So we published this last year, 2023 now. But basically, we showed it extends lifespan in a dosage-respondent manner. So here you have, this is worms, so this is their survival and days. In black, you have controls. And then you have a dosage-respondent effect up until 200 micromolar. And above those dosages, it doesn't extend lifespan so much or stop extending lifespan. And it works whether you feed animals early in life or later in life. I mean, we did a number of other experiments. We think it works via autophagy, which I'm not showing. So we did other studies as well. The only other thing I would point out was that in collaboration with Colin Hewell, which I think is here, although in another panel at the moment, and also Vadim was there. So this project, we did it in C. elegans, but also particularly in Vadim's lab, they looked at transcriptional changes in mice fed rilmanidin and showed that there is an overlap with other life-extending interventions. So you know, we argued that it's a promising new geroprotector, and given that it's already used in a clinic to treat hypertension, it may have other broader applications. And you know, my goal would be to do a small clinical trial in humans to test if it has, besides obviously the benefits for treating hypertension, if it could have other clinical benefits in human beings. So the other topic that we're doing a little bit of work, and we've heard about this already, so I'm not going to spend too much time on it, is in cellular rejuvenation by partial reprogramming. So I mean, many people have mentioned this already, but just so if you're not aware, we can use Yamanaka factors or different combination transcription factors, not just to turn cells into iPS cells, but also to different methods, but essentially to partial reprogram cells, which allows to rejuvenate, at least according to most markers, allows you to rejuvenate cells in vitro, which was developed by, well, initially in the Salk Institute by Alejandro Campo and Juan Carlos Belmonte and others. So we've been doing some analysis on computational analysis of this as well. So essentially looking at the gene expression profiles of the induced reprogramming and comparing it to iPS cells, and then trying to predict new genes, trying to predict new regulators that would be more specific to cellular rejuvenation as opposed to dedifferentiation, and ideally also trying to make predictions of compounds that would induce cellular rejuvenation. I mean, Dante, who's sitting right in the front row, he recently finished a master's on focusing on this, and now other people in the lab are continuing the same analysis. So essentially, applying some of the same methods we've used before to prioritize and identify new genes and regulators and drugs that modulate aging and longevity, try to do the same, but more specifically for cellular rejuvenation. So that's something we're trying to do. We also, as I said, I'm CSO of Youth Bio, which is a US-based company. And the focus of the company is on partial reprogramming and developing gene therapies based on partial reprogramming and different combinations of factors to restore youthful profiles. And particularly, we're starting with single oral therapies. I mean, we heard a wonderful talk already before today about the importance of cognitive health and how we need to target cognitive aging. So starting with conditions like Alzheimer's disease. I would invite you to visit our website for more details on that. So, and I still have a few minutes. So in the last 5 minutes, I'll focus to a different topic, which is, I don't think has been mentioned already today, well, at this conference, as far as I could tell, although I wasn't in all the sessions. Which is another longevity healthspan technology, I would argue, which is organ preservation. So you're probably aware that there's big limitations in terms of our ability to cryopreserve human organs. We cannot cryopreserve large human organs like hearts, lungs, livers, kidneys, and so on. It's not possible to do so. And this is a huge limitation, a huge medical bottleneck. Because what happens is that when someone passes away, for example, in a car accident, and they're an organ donor, you have a very limited window to find a suitable recipient for that organ. And what it means is, for example, for hearts, only 30% of organs are actually transplanted. only about 20% of lungs are used. So that means there's this huge wastage of human organs for transplants that never reach the patients that really need them. And that is a very big limitation, a very big medical bottleneck. And as I'm sure you're aware, there's massive waiting lists for organ transplants. Many patients die while they're on the waiting list because they could not get a suitable organ. So from a medical perspective, I mean, this is data from Sebastian Giwa, who they published in Nature Biotech some years ago. They calculated that, well, we have this huge demand for human organs, and this is a major medical issue. So they estimated that for the United States, this is data from the US, that we could save hundreds of thousands of lives, or could be prevented hundreds of thousands of deaths if organ transplants were available without any constraints. So their estimate is that it could prevent over 30% of all deaths in the US if we could have organs available without any limitations. And it could double the likelihood, they estimated it could double the likelihood of living to 80 years of age, again, if we had organs available on demand. Which I think would be quite revolutionary. I actually don't know for sure. I think it's a fascinating work, for example, Vadim is doing in different, looking at aging of different organs, regarding how much rejuvenation you would achieve if you could transplant young organs into older patients on a almost systematic basis, or systematic is not the right word, but you know what I mean, maybe in a more regular fashion. So the point is that the take-home message, this would have huge medical benefits. And so we've started focusing on this some years ago, and again, I don't have time to go into a lot of details, and most of this is still in the beginning, but what we're trying to do is trying to apply, again, some of the same computational analysis, machine learning, AI technologies that we've successfully used in aging and longevity. We're applying that to study cryobiology, specifically to study cryoprotectants. So we know there's cryoprotectants, essentially antifreeze compounds that protect organs from damage during cryopreservation. And we can study their molecular profiles, and then we can try using our computational methods, try to predict new cryoprotectants, new toxicity neutralizers, and try to ultimately develop new cryopreservation methods for cells, tissues, and organs. So as I said, we started this company about a year ago, called Cryo Technology, and we're looking to use these computational tools to create new methods, new protocols that will allow us to improve cryopreservation of cells, tissues, and organs, for which there's a huge commercial interest and also medical applications. And so we're looking for usual collaborations, investors, partners for developing these cryopreservation technologies. And so with that, let me summarize. As I mentioned at the start, we do have made some progress, and we're generating lots of data. There's this huge avalanche of data that we as a community are generating from omics approaches. From a pharmacological perspective, we know of over 1,000 longevity drugs currently in our drug age database, which is quite remarkable, with the caveats I said of, these don't actually have that big effect sizes. None of them has really surpassed caloric restriction, which is still the most we can extend lifespan in preclinical models. And hence the need to better understand aging. That's, I think, a very big gap we still have in the field. We don't have a good understanding of the aging process, which in turn affects how we're going to target something if we don't fully understand it, what sort of biomarkers we're going to use, as we heard in the morning, and so on. So there's a lot of constraints and challenges in the field because our knowledge of aging is still somewhat limited. I would say largely limited. And then, of course, we have various challenges, the human translation from preclinical models that apply to big pharma in general and drug discovery in general, but they apply in particular to our field of aging and geroscience, which are still major limitations. And so in spite of this challenge, the big promise of using these different computational network systems, biology methods, machine learning, AI, the big advantage is that it allows us to target or allows us to tackle the complexity of biology and allows us to predict promising targets, promising genes, promising pathways, and even drugs to target the aging process. That's something that we showed empirically, for example, at the level of cell senescence, for example, level of new longevity drugs like rilmenidine, which is a new geroprotectant that extends lifespan in C. elegans and is already approved for human clinical use. And last time I told you about cellular rejuvenation, which are trying to identify new genes and compounds, just as I'm sure you're aware, many of the labs and companies, and also our ongoing goal in developing new cryopreservation methods, which again argue that it has a huge potential to improve human health. So with that, let me just finish by saying, just going back a little bit to the goals of the conference and architecting the future of human health span. I mean, I think it's clear that there is a lot of interest in the field of aging and neuroscience in developing new interventions for aging. I think that's brilliant. And as the field continues to grow and develop, I think it's very clear that we do need these computational machine learning AI approaches. And their role, which is already important, it's only going to grow in importance. So I mean, I advise all my students in the lab and trainees and postdocs to learn computational techniques, even if they do primarily experiments. And clearly, the more embedded we're going to be with machine learning approaches and computational analysis, I think the more productive we're going to be as well in the future, and hopefully make important discoveries for the field. So with that, I'd just like to, so I'm based at the medical school in Birmingham, actually. So this is, I'm actually based in the hospital. That's right there. That's my office is there inside the hospital. And I would just mention Alexei, who's been working on the machine learning approaches and analysis. And also Angelo as well, who's did some data development. I mentioned Dante as well, and Alex, who's now doing quite a lot of analysis also of cellular reprogramming in our lab. I mean, all of our preprints and PDFs of our papers are available on our lab website. You're welcome to visit. If you have a question or want to follow up, feel free to drop me an email. And of course, we thank our funders as well for the support for this work. And thank you very much for your time and attention. Thank you. 2 minutes ahead of time, so we have.
That was an amazing talk.
Thank you.
My question is specifically around sort of the training of the models and the data quality that is undergoing these models. So a lot of the data that you're using is publicly available data, and some of the data, of course, is not as high quality as others. Of course, something like ITP is a lot more high quality, while something maybe in drug age, for the same compound, you have multiple different median lifespan extensions. So how do you sort of get that sweet spot between sort of getting a good data quality, yet still leveraging publicly available data so that your models are high quality?
Yes, no, that's a great question that we've been struggling in, you know, ever since I started doing. I mean, we've been doing machine learning for 15 years, so we've been struggling for addressing that for a long time. I think conceptually, I think if you have a strong enough signal, so this is my approach ever since I started doing meta-analysis 20 years ago of transcriptomic data, is that if you have a strong enough signal, even if you have some bad apples there, if you have some strong enough signal, you can find it, even if you don't have suitable data. Having said that, you obviously have to do some filters. So if you have something that looks clearly different from everything else, then you can address it statistically and also biologically. So I think there's two considerations. There's a biological consideration. What are we trying to find? If you're trying to find, I mean, I think the longevity drugs is an interesting one because you have drugs that extend lifespan, medium lifespan, but not maximum lifespan. So you kind of wonder, is that really retarding aging? Is it just affecting cancer? I mean, I think it raises a lot of questions. So I think that's, you know, if you have to decide what's your goal. I think for the C. elegans data, for example, we did have hundreds of data points, and that's okay. So you also have those constraints. For the cell senescence analysis that I mentioned, we had hundreds of experiments. We could, you know, be quite confident. For the mammalian data on longevity drugs, it's a bit more tricky because we don't have that many data points. So unless there's something that we're not comfortable with, there's a lifespan extension, but it's not statistically significant, in which case we exclude it, then we tend to include more data than less. But in the end, as you say, it's about finding a balance, and I do think it varies analysis by analysis, depending on one, what you're trying to discover, your goals, and two, what's the underlying data to begin in? What do you have to begin in? How much data you have, and what's the quality? But that's a great question. Yes, Joris.
Yeah, so I was wondering about these overlapping signatures that you identified in the mice, for example, in the transcriptomics. So the fact that all these drugs lead to this overlapping signature, but we don't actually see that many of those drugs do something in humans, or we don't have the evidence yet. Do we actually already have evidence that this transcriptomic signature at least is something that is translatable to the human so that we can use it as a screening tool? Or do we need to create novel kind of transcriptomic signatures based on human data that we can use, for example, in the mice for the drug screening? So how is that at the moment?
Yeah, that's a good question, and it opens a bit of a Pandora box of issues. Okay, so I mean, I have a little experience with transcriptomic signatures. I've been doing it for a long time. I mean, my take, for example, from the first meta-analysis I did when I was still in Boston, actually, of aging signatures, again, is that if strong signals you'll find them across species and you'll find them across organs. Because the other thing you didn't ask is, maybe the transcriptomic signatures you're finding in the brain is not the same as you're finding in the skin, right? And there's an overlap, but it's not the same. So the stronger signals you generally find across organs and you find across species. Inflammation, immune system responses, you tend to find those quite well conserved. And maybe those are the ones that underpin, I mean, I think there was a question today is in the biomarkers session, maybe that underpins some of the clocks, maybe that underpins some of the drugs, for example. Although in the drugs we do have, you can go a bit more granular and see which drugs target which particular pathways, for example. So I think that is an issue, but empirically we do know that there are some conserved signatures across species and across organs, and we can use those. Now then again, it depends a little about what your objective is. Actually, the natural pharmacology we did not use rodent data. We used data from monkeys, most of all. From Rafa de Cabos, from the NIA. So that's data we use. So it was actually not mouse data, it was monkey data that we use, which is more similar to humans. But then, keep in mind, we actually tested our compounds in C. elegans, not even a mammal, and most of them extended lifespan. So I think the take-home message, not just about the signatures, is that yes, there are some conserved aspects, like inflammation, like immune responses, which allows us to look at these signatures across organs and across species that we can detect and we can use. For sure, there's going to be tissue-specific signatures and species-specific signatures, and we should focus on those as well. But that I think is another line of research that, yeah, I mean, I'm all for finding all kinds of, to use a term from an older paper, private and public mechanisms of aging.
So I know that you think in evolutionary terms, and I'm curious how you think about the cellular reprogramming, where there's a set of genes that would be easily accessible for evolution to modify, that can make cells look younger, but for some reason evolution has not produced this. And does this lead us to something kind of similar to the cellular senescence paradigm you mentioned, where we might not always want to do that, or is there something else going on here?
Yeah, that's a good question. I didn't really mention much about evolution. I mean, we had the comparative biology session yesterday. I mean, the partial reprogramming, the reprogramming is to some degree conserved between at least mice and humans. I think Alejandro did some recent experiments actually in C. elegans of partial reprogramming, and they shortened lifespan, if I remember correctly. I don't know if anyone remembers, but I think there's a preprint on it. But it's quite different, of course, C. elegans to mice and humans. So there is some level of conservation between mice and humans. In terms of partial reprogramming and Yamanaka factors, right? Which, makes sense because, this going from, an adult organism all the way to unborn and all the way to a fertilized egg, it is something that happens to all mammals, right? So that it makes sense that there is some evolutionary conservation at that level. Even though I would assume that maybe some of the genes that are playing a role are not exactly the same. That's kind of what you expect. That there's a broader mechanistic overlap, but there's going to be some distinction between it. So my assumption has been that there is some, at least fundamental conservation of cellular rejuvenation between mice and humans. And I think that's kind of how the field is going. I would imagine there would be some individual genes that are different. Well, I actually think it's more, I was talking about this just earlier today with Michael Ringer, is that what I think is, in my opinion, is that the Yamanaka factors are a blunt instrument for cellular rejuvenation, and we and many others, different companies and different labs, are looking for better ways of inducing cellular rejuvenation without the differentiation. But what I think could well be the case is that you do need, and I would hypothesize it is that you do need different factors for different organs and different cell types. And so you may have some overlap, but then you're going to have to need like something specific for the liver or for the brain, particularly between post-mitotic and mitotic tissue. So that's what I think is going to be a bigger challenge, but also a big opportunity, because maybe we can't find one way of rejuvenating everything, but we can find one set of factors that rejuvenates the brain. Hey, we can we can develop therapies for Alzheimer's. That's how I think. I think he was first, but
okay.
Yes, go ahead.
So you mentioned it. You mentioned it already several times that dietary restriction is the golden standard, and all of the other drugs, they may extend lifespan, but not to the extent that dietary restriction does. So, would it make sense to take also dietary restriction transcriptome and proteome data as the golden standard, and then see whether dietary restriction in young versus old doesn't matter because it works over the whole lifespan? So to see whether you can approach dietary restriction data with other treatments. So instead of taking all the agents that do something but may work very differently and may confuse your outcome, you could start with something that we know works in all organisms, in all organs for the whole lifespan period. So if you would take that as a starting point, would that be more productive?
Yes. I mean, so we've done quite a bit of, actually, we've done some transcriptomics of caloric restriction in the brain of rodents. And actually, our network pharmacology, I didn't go through the details, but the network pharmacology we did, initially, it was from monkeys, as I said, under caloric restriction. I don't know if I think they were young animals under caloric, or relatively young animals under caloric restriction, and that's the transcriptome that we used in order to do our drug repositioning. So it was actually from caloric restriction. We've done transcriptome analysis of other interventions like rapamycin, for example, but we have done quite extensive transcriptome analysis of caloric restriction. We published in Genome Biology, I think 2015. Shona Wood was a brilliant postdoc at the lab, did this analysis. We published, for example, showing that caloric restriction ameliorates a lot of the aging changes you see in normal rodents fed ad libitum, for example. So we show this at the transcriptome level. And again, we can use that for then various downstream analysis. I mean, there's still the question of whether caloric restriction works in human beings. I mean, yes, I think it is the gold standard in rodents. I mean, the high TP haven't done caloric restriction, which I think is a shame. I think they should do it anyway.
I'll show in the next lecture.
Looking forward to
children,
it.
Yeah.
The only thing I would say in terms of humans, because we don't know if caloric restriction works in humans, I would argue that the gold standard in humans is exercise. And to me, that's the gold standard, right? And the question to me is, do we have any intervention, including rapamycin, that on caloric restriction, that are healthier or extend health span more than exercise? And I don't know that. No. To me, that still remains an open question. So the gold standard in humans, to me, is still exercise.
Thank you.
Yeah, thank you.
Hello there. My name is Maria Angelis. I'm a physical therapist, and I also take rapamycin for the last 2 years. I've also taken urolithin. I exercise, and but I started out doing the fasting, and I did it for a while. However, I had a problem that could not be resolved by a doctor's visit, or more than one, for that matter. And but I noticed I had a problem with my feet. They were swelling, and I did every test. Being that my husband is also a doctor, he did every test, making sure that he canceled out every possible scenario. What I noticed is that I no longer have this problem after I've taken urolithin. But I'm not sure now because I've done so many things, exercising, fasting, rapamycin, urolithin. But all that together, long term, because it's been almost 2.5 years now, for some strange reason, my feet swelling went completely away without making no dietary change whatsoever. So I'm wondering, what's your take on urolithin as a golden standard together with everything else? Because I noticed that the last thing I took, which had a great effect on my legs, was urolithin A, which is supposedly taken from pomegranate. But even if you drink pomegranate, from what I know, if you don't have the gene to convert the pomegranate to urolithin, you can drink all you want. You will not benefit from pomegranate. What's your take on urolithin?
Well, thank you. Well, the short answer is that we haven't done any work on it, and I've never taken it. So personally, I'm very conservative about what I try. I've never done fasting or caloric restriction or rapamycin. I do exercise. That's the only thing, because I think that's the gold standard, and I don't smoke. so that's kind of what I do. I think, but if you're doing many different things, it's also difficult to entitle, like Brian Johnson. You're doing so many different things. Even if it helps in some way, you're not going to be able to pinpoint what helps. And if something is having side effects, you're not going to be able to tell exactly what is having the negative side effects. So I think that's the risk. So yeah, it obviously varies from person to person. And of course, this is not medical advice, but I think personally, I'm quite conservative in what I try, and I don't even have the healthiest of diets, I have to admit. If there's some ice cream outside, I'll go for it.
Thank you very much. Enjoyed your talk. My name is Asim Al-Fadda from King Saud University. As an endocrinologist, we deal a lot with patients with diabetes and obesity, and we use the glucagon-like peptide-1 receptor agonists for several reasons, and the data is coming to show that it's beneficial for many other reasons more than diabetes. Do you have any strong data that these drugs might improve longevity or healthy longevity in humans?
Sorry, which were the drugs?
The glucagon-like receptor 1 agonist, GLP-1 receptor agonists.
We don't have any data ourselves. I think that, I've been, as you know, there's been quite a lot of interest in those drugs. My take is, I think if you put a whole population like the US on those drugs, I think it will have benefits because obesity is such a big problem. I think the question is, how does that compare to exercise? That's one question. And is it actually reversing aging, or is it just improving health in patients that are obese, for example, or patients that have a clinical condition to begin with? And I think that's an issue in itself. What is a normal human population? Are we normal? More people die in the world of overfeeding than undernourishment right now. Is that normal? I don't think it is. So I think that it opens a lot of questions of what is a normal human population and whether those sort of intervention will reverse aging or simply improve health or reverse an unhealthy habit or diet or obesity. Does that answer your question?
Yes, I think we need to do more research on that because we see the benefits of these drugs even for people without obesity. It has data now on cardiovascular risk, kidney protection, osteoarthritis, maybe also some patients with cognitive deficits. So I think maybe more data need to be accumulated before as I agree with you. But these are very interesting drugs, I think, nowadays for many fields of medicine.
Okay.
Thank
No,
you.
no, I think that absolutely, I completely agree. I mean, if you know, lean individuals who exercise also have benefits, then that would be quite remarkable. Yes, absolutely. Thank you.
The question is
Hi.
here. Just quick question. So you haven't mentioned an age database, which is like an amazing database that the entire field uses. I wonder if you have plans to expand it extend or add new species and data. And the second is, what are the cryopreservation approaches that you think are promising? Because it's really a major challenge in cryofreezing.
So regarding NH, so our funding to develop NH expired more than a year ago, so we don't have plans or funding or anything I mean, I'm just fingers crossed the server doesn't crash, because if it crashes and I don't know how to fix it, it just goes offline. We try to apply for funding, including from Hevolution, and nobody has given us any money to continue working. So unfortunately, we cannot further develop it without having the support to do so. What was the second question?
Cryopreservation approaches.
So to me, I mean, I think there's different ways of going about it. I think for the cryopreservation, I mean, we're trying to do it more at the cell level at the moment, so doing computational analysis and try to improve cell cryopreservation. The goal, of course, is to eventually go to larger tissues and organs. That's the idea behind it. But at the moment, we're essentially trying to develop new chemical formulations. So it is almost like a chemical biology or computational chemistry approach of trying to identify new compounds or existing compounds that could be repurposed for improving the cryopreservation methods. That's kind of how we're going about it. Yes. Thank you. So if there's no other questions, then I think we're right on time. Actually, we're 1 minute ahead of overtime now. So, all right, well, thank you very much for your time and attention. Thank you.
Now it's okay, yeah? Great. Thank you very much for the kind invitation to give the opportunity to talk about work that I've been doing since 1981, starting not in the aging field, but now being very important for understanding aging and for influencing the process of aging. So, what I would like to do is to explain to you the importance of DNA damage for aging, and also what nutrition can contribute in influencing the process of aging itself. So we started not working on aging, we worked on DNA damage and DNA repair. And that's what I would like to start, the connection between DNA damage and aging, and then later talk about the effect of nutrition on DNA damage and aging. So I am affiliated with 3 research institutions. One is the Erasmus Medical Center in Rotterdam, already since 1981. I'm still affiliated with Erasmus. After my retirement in 2016, the results of research were so promising that I expanded in 2 other locations. So I started a new laboratory in Prinses Maxima Center in the Netherlands, in Utrecht, on children with cancer. You'll learn out later why. I also started a new laboratory in Cologne, the CCAT, and I'm also part of the Oncode Institute, but I have no commercial interaction, so I'm completely free to talk about everything what we have been doing. So I'm working on DNA damage, and DNA damage is a fundamental problem for life, because DNA is constantly damaged. It's damaged from outside, UV, radiation, numerous chemicals in food, in water, in air, enter our body and may have an effect. But a very important other source of damage is endogenously. Our own metabolism generates reactive oxygen species, alkylation products, mechanical stress. When the cell changes shape, the nucleus wants to retain its shape, but also will have some flexibility. So mechanical stress causes DNA damage. Water, every single day in every cell of our body, 10,000 bases are damaged simply by hydrolysis. So we think that on average, every mammalian cell may experience up to or even more than 100,000 damages that inflict DNA structure. So, for instance, you can see UV causes this type of damage, breaks bulky adducts, A-basic sites, interstrand crosslinks, intrastrand crosslinks, all thousands of different types of damages are induced in our DNA. And of course, DNA is vital because DNA is used for general transmission of genetic information and for its use. So if you have damage in your DNA, then your metabolism of DNA will be affected. And one of the already long-known consequences of DNA damage is if you have damage in your DNA template and you replicate, you have a higher chance that you make a mistake, a mutation, or a break that persists. So you get mutations and chromosomal aberrations. And this is the main cause of cancer. So cancer is also aging-related. The most important risk factor for cancer is your age. So if you build up more damage, then you build up more mutations, and more mutations lead to oncogenes that become activated, tumor suppressor genes that become inactivated, and you get cancer. This is the most important factor to determine cancer. But particularly our laboratory has tried to understand what other effects DNA damage may have. And if you have, for instance, a DNA interstrand crosslink, then if you want to transcribe a DNA, you need to separate the 2 strands, but they are covalently coupled. So you get transcription stress, that's indicated over here, but you also, with replication, you have replication stress. So cells respond to that, by stopping transiently the cell cycle. If they are proliferating, they, time out, try to fix the damage first before continuing and making a mutation or a chromosomal aberration. If the damage is too severe and the cell cannot repair it, then it will never divide. So you get cellular senescence. This is one of the main causes of cellular senescence. So, and also if transcription is affected, and particularly I'll show you later, longer genes have more damage than very small ones. So the longer genes with aging uniformly go down. So you get transcription stress, you get functional decline, too much damage can also trigger cell death. And we think all of these are the main drivers of aging. And I'll show you the evidence that we have for that in my presentation. Fortunately, we possess a very intricate network of repair systems that tries to deal with this problem of DNA damage that's constantly there every day, every cell. So before I'll talk about repair, because that is what we started with, DNA repair, to understand DNA repair, let me make one important point. So there are many different types of damages. So there is not one repair system that handles all of those different lesions. So there are dedicated pathways for subsets of DNA damage. So for instance, nucleotide excision repair, a process that we started working on already a long time ago, that deals with any type of damage that distorts the base pairing between the two strands, so that you get your double helix is deformed. That is, so UV can induce that, but also numerous chemicals distort the helical structure, and then nucleotide excision repair tries to help out. I'll show you how it works. Transcription coupled repair, so if you are transcribing a gene, making an RNA copy of a DNA of a gene, then the RNA polymerase can stumble upon a damage, and it can be blocked by the damage physically. So there is a dedicated repair system that monitors how transcription goes on in the cell, and if transcription in one gene is blocked, then that system helps out, pushes the polymerase back, tries to repair, and then allow transcription to resume. So that is how we constantly clean the most vital part of the genome, namely the ones that is used for the cell to transcribe to make proteins. So also many of the damages that that also are repaired by this system are also target of transcription coupled repair. So other systems, other types of damages are repaired by other pathways. Base excision for subtle lesions. Double-strand breaks are very difficult for cells to handle, so there are multiple pathways. Homologous recombination, non-homologous end joining, single-strand annealing are just a few of those pathways that try to handle a double-strand break. Interstrand crosslinks, again, multiple pathways. Hundreds of proteins are involved in these systems. So before, I'll highlight the top two, because we are working on those for a long time, have made major contributions in understanding how they function, but they stand for the whole problem of DNA damage that is constantly inflicted. So, however, it's very important to realize, even when we all are hopefully born with potent repair mechanisms, but even with potent normal repair, some damages are very difficult to find by repair. Sometimes some damages are so severe you cannot repair them. Sometimes repair is there just too late, or repair makes mistakes. And I'll show you why, every cellular process with aging gradually declines. Also, repair will decline with aging. And so, nevertheless, even though we are born with potent repair, in the course of time, inevitably, you will still get lesions that accumulate, mutations that accumulate, cancer that is the consequence, and or cell death or malfunction is another consequence. I'll show you why we think that's the case. But if you happen to be unfortunately born with a defect in a repair system, then all of these consequences take less time. It goes faster. And I'll show you also in a minute. So Nucleotide excision repair, that's the process that we started on. We were the first in the world to clone a human repair gene, and we have cloned almost half of all of the genes that are on the pathway that are important, or co-identified them with others. So we have made major contributions in this understanding how this mechanism works. And it works in a very logical manner. So if you have a damage, for instance, a UV damage that is induced by UV light in the sun, in Saudi Arabia more than in the Netherlands, then there are proteins that are constantly monitoring DNA for whether it's properly base paired. There's a protein that we discovered, that's the XPC protein, that is binding to DNA, dissociating, but it has a finger. It wants to put its finger in between the two strands. If the two strands are properly base paired, it cannot. But as soon as the base pairing is disrupted, XPC binds, sticks its finger in between, and then there is a complex of 10 proteins that we also discovered together with a French group, TF2H, that has two helicases, the XPB and the XPD helicase. Oh, sorry, that is something that I don't want to. So XPB and D helicase, they open the DNA. Another protein, XPA, verifies is there really a damage or not. And then there are the surgeons, the ERCC1, XPF, and XPG, that are nucleases that cut out the piece that contain the damage, and then the gap is filled by replication machinery. ERCC1, I'll come back to that. That was the first human repair gene cloned in our laboratory. We cloned also XPF. We cloned also many of the other genes. So we have made major contributions in trying to understand and dissect how this molecular mechanism of repair works. There is one problem. Some damages are very difficult to be recognized by this system because they are not distorting enough. XPC doesn't get its finger easily in between. So those damages persist for days, maybe weeks in the DNA. So, but if they happen to occur in a gene that is being transcribed by RNA polymerase, it stumbles upon such a damage and blocked, cannot continue. So then there are proteins that are constantly monitoring how the progression of a polymerase is ongoing. And the CSB protein, which we also cloned in our laboratory, the CSB protein is very important to monitor elongation by RNA polymerases. If it's stuck, then CSB binds and recruits the repair machinery, try to fix the damage. And then, again, TF2H opens the DNA, and XPA verifies, and the endonucleases, the surgeons, cut out, and then the DNA is again. This is how transcription is rescued when there is damage that blocks the transcription machinery. Okay, so that's transcription coupled repair, and that's global genome repair, how it works. Now, there are children that are born, very, very rare diseases, where they are born with a defect on any of those genes. So all the genes that are indicated in pink, XPC, XPE, and so on, we know there are children that have a defect in those repair genes. And then we see the consequences. I'll talk about them in a minute. But what we have done, and we have made virtually all the mice in the system are made in our laboratory in Rotterdam, we have made mouse mutants. All the proteins that are indicated with an M, we particularly, almost all the mice have been generated in our laboratory to try and find out what happens if you lack that repair factor. And the results are really amazing. I promise if you leave this room and you stay till the end, you will never forget this lecture in your life. Because I'll show you what happens. So first, the diseases. Very rare. XP stands for xeroderma pigmentosum, a dry, pergament-like, actually aged skin, because these children and patients are exquisitely sensitive to sunlight. 5 minutes in the full sun, and they have sunburn. And also show, by the way, accelerated aging. And you see pigmentation abnormalities too much, and other places too little, in sun-exposed parts. That is the hallmark of XP, but most importantly, these patients have more than 1,000-fold increased skin cancer. And this is apparent already here, but if you look, children, if they are not exquisitely protected from any sunlight, they will get skin tumors already by the age of 7. And this is a mild child that was not detected in Lebanon and that had not been protected, and you see already. But there are children that are literally 10-fold more tumors at this age. The whole face is totally full of cancer. So cancer is the outcome, and so there is, if they are really exquisitely protected, they are moon children, they're called moon children. If they are exquisitely protected, they can become 40. Then they get other types of cancers too, and other problems, but there is relatively normal development. And this is always due to a defect in the global genome system, in damage everywhere. That is, XPC, the protein that puts its finger. If that is defective, then you get this disease, or that pathway. Now, another disease, which is very peculiar, and that is also rare, it's called Cockayne syndrome. And these children are almost the opposite of the XP patients. No Cockayne patient has been ever recorded to have cancer. But instead, they have very severe neurological and developmental abnormalities. This is a French patient, Baptiste, and you see already also UV sensitive. They are all UV sensitive because UV light causes damage and they cannot handle that well. But see, they had very neurologically already a little bit abnormal. But now look, 4 years later, he needs glasses, he needs hearing aids, he cannot walk, he cannot talk. And Baptiste, on average, these children get 12 years on average. But Baptiste became only 10. And this is Baptiste in the year that he unfortunately died. This is his sister next to him, 1 year older. So you see dramatic growth retardation and devastating disease, no cancer. But yeah, they get only 12. So yeah, we don't know that. This is always linked to a defect in transcription coupled repair. That other pathway that helps out when transcription is blocked by the damage to try to fix that. So, and now I show you yet another disease, which is even more puzzling. And that's called trichothiodystrophy, TTD. These children have something very peculiar. They have brittle hair, brittle nails, scaly skin. Well, with that you can still become 80. But many of these children don't get older than 5 or 7 years. So, and they have many features in common with Cockayne. And there is a defect in the two pathways together. It's not a complete defect, it's always a partial defect. So, how can it be that you have so many different phenotypes with a repair defect? How can it be? You can have even a mutation in one gene. For instance, the XPD was one of the proteins that opens the DNA, the helicase function. Well, if you have a mutation in XPD, you can have XP, you can have Cockayne and XP, you can have TTD, brittle hair, you can have TTD and XP, and you can have another disease, which is called COFS, cerebro-oculofaciosskeletal syndrome. These children do not get older than 1.5. So one gene, cancer, neurodegenerative diseases, and many other problems, short lifespan, and brittle hair, how can that be? How can that be? So one way to try to understand what is going on is to try to make a mouse with precisely the same mutation as a patient has, and see whether that mouse can help us to see what happens in these children. So that's what we embarked upon. That was not that easy. So we have made many mice. You saw many M's, but I'll show you the TTD mouse because we are the only ones that were successful in generating this mouse because it was a very delicate operation. But we succeeded. I'll show you the TTD patient and now the mouse. And the mouse has precisely the same point mutation in XPD as the patient has. At position 722, DNA encodes arginine. That's the R. But unfortunately, there are a number of children with a mutation at that codon, and now it codes not for R, but now for tryptophan. And if you have that mutation, all these children have brittle hair. And you see, also the mouse has brittle hair, scaly skin, brittle nails. So in that regard, the mouse is a very good model for at least those phenotypes of these children. But of course, brittle hair is trivial. And we understand precisely why the hair is brittle and the skin is scaly and the nails are brittle, but that is trivial. We want to know why are these children living 5 years and you don't develop and so on. So that's where what we further investigated, and so there are striking. This is really a very exceptionally good model for the human disease that we find in the mouse. And then we found something that was an eye-opener at that moment, because nobody had linked TTD with aging, but the mice became gray. Oh, are they aging? This is a very puzzling rare disease, and a patient, one physician sees only one patient, so wow. But now we look, are they aging? We were not experts in aging, so now we entered the aging field, so we had to learn more about aging. Well, this is not an aged mouse, but we had to find out, how an aged mouse looks. And maybe you have never seen an aged mouse, but I'll show you now one. That's on the next slide. So it gets kyphosis, it becomes gray, has an overall frail phenotype. We looked in the brain, in the liver, in the kidney, in the skeleton. No question, there is accelerated aging in this mouse, not for all the tissues. It's segmental. So it's only a part of the body that is accelerated in aging, and paradoxically, some organs have delayed aging. We can compare the genetically identical wild-type mouse with the one that has this one mutation. They are born at the same moment, have the same food and whatever, and still we see a split aging phenotype. So particularly the post-mitotic tissues, the ones that do not cell renew, those are the ones that are accelerated in aging. And I'll show you a little bit some of the phenotype, some of the characteristic phenotypes. So they have a reduced lifespan. They live about 1.5 years instead of 2.5 that mice wild-type mice can become. They show cachexia, sarcopenia, early infertility, cutaneous symptoms, skeletal abnormalities. You saw the kyphosis already, and subcutaneous fat. There is progressive neurological abnormalities, which is severe. Lymphodepletion, thymic involution, liver and kidney, unequivocal features of accelerated aging, but not all organs. The hemopoietic system, not so much. Cataract in the eyelids, even less. Less cataract than the wild types. And we can explain it all, I'll show you later. So, and in terms, in patients, indeed, some clinicians had looked and seen, oh gosh, it looks like this child has something that looks like osteoporosis. But of course, you cannot make a conclusion on one phenotype, so you have to investigate actually all the organs. We can do that in the mice, we cannot do that in patients. So, but there is no question, TTD was an unknown progeroid DNA repair syndrome. So, mice and humans are not the same, but the TTD mouse is an exceptionally accurate model for the human disease. Actually, we found clinical phenotypes in the mice first. We contacted the clinician with the patient. Can you have a look at the kidney? Can you have a look at the liver? Because we see aging in the liver and the kidney. And then he looked, oh gosh, you're right. So indeed, this mouse is an exceptionally valid model for this very rare disease. But what we can do with mice is we can cross mice. So we made other repair mice. So this mouse still became 1.5. So we thought, what happens if we make the repair defect more severe by crossing in another repair deficiency? That's what we did. So we crossed the XPA mouse with the TTD mouse and see what happens. That was an eye-opening observation. This is the XPA mouse itself, cancer-prone, a little bit of neurodegeneration at later life. But if you keep it from UV, then it can still become 2 to 2.5. The TTD mouse, on the other hand, is losing hair, brittle, has early aging, actually has less cancer, more aging. So that mouse lives about 1.5 years. And this small mini mouse is the double mutant. Has both defects, XPA as well as TTD. And now this mouse lives only 5 to 8 weeks. So aging normally in a mouse takes 2.5 years. The TTD single mutant 1.5, but the double mutant lives 5 to 8 weeks. So if the single mutant is accelerated aging and we make the repair defect more severe, then this must be aging too. So, but then aging compressed in a very short period of time of 5 to 8 weeks. When we published this in Science, many people in the aging community never believed that, you know, yeah, these children are sick and these mice are sick. They die, but they are not aging. Now, there were even satirical poems published about our work in Aging Cell. But now, the students of the person which wrote those poems is also using our mice. So these mice are really accelerated in segmental aging. I'll come back to that in a minute. So there is the severity of the repair defect correlates with an acceleration of a still segmental aging phenotype. Now I'll show you a mouse. We have made many mice, so we have others. We have made CSA and CSB mice. We have made XPG mice, for instance, XPB mice. And they all have the same phenomenon in terms of aging. The more severe the repair defect, the faster the aging takes. But it's not full spectrum wide aging for all the organs and tissues. Now I show you a mouse. Let me first explain it. So if you have a defect in global repair, like in XP, then there are many damages that persist in the genome. However, if transcription-coupled repair is still functioning, then all the damages there are more damages that are blocking, but they are all repaired. And transcription is needed for survival. So then transcription-coupled repair keeps a damaged cell alive, because the damage that is present in the non-transcribed strand is not repaired with transcription-coupled repair, and the DNA elsewhere in the gene is not repaired. So you keep a damaged cell alive. If you do that, you get more mutations and you get cancer. So that explains why a defect in global repair only leads to cancer, because the cells survive because transcription-coupled repair is still allowing the cell to live. Now, if you have a defect in the other pathway, in transcription-coupled repair, so then there is a small amount of damage already interferes with transcription. Transcription is essential. So you now trigger cell death at an early moment. So a dead cell will never give rise to cancer. So you overprotect from cancer at the expense of too much cells dying. Too much cells dying accelerate aging, so you get the balance between cancer and aging is disturbed. If you have a defect in transcription-coupled repair, you overprotect from cancer at the expense of too much aging. So, and if you take now, so the cells will die, function decline, cancer goes down, but aging goes up. So that explains why cocaine TTD children are showing accelerated aging. Now, if you have a defect in the double mutant, which lives only 5 to 8 weeks, then there are many damages that would have otherwise been repaired by global repair that persist. So now the problem of transcription-coupled repair is much more accelerated. So now you get much more cells that die and functional decline and give aging, and that explains this dramatic accelerated aging that I showed you in this double mutant. Now I show you a mouse with 4 repair defects. This was with 2, but now I show you one which has 4 repair defects. And that's this mouse. And that's the champion of aging in mammals that we know. This is the ERCC1 mouse, because ERCC1 was the first repair gene cloned in our laboratory. We were the only ones who were able to make a hypermorph of this mouse. So it's not a full knockout, but a hypermorph. And this mouse is alive and shows aging everywhere, because now other repair systems that are important for cells that renew are also affected. So now also tissues that have renewal have a problem because of a defect in ERCC1. And this mouse shows, as far as we can tell, and others too, many people are using this mouse now, aging everywhere. So this mouse can hear when it's born, can see when it's born, but then becomes blind and becomes completely deaf, the high tones frequencies first. So the mouse gets tremendous cognitive decline, tremors, ataxia, imbalance. I will show you with movies later. Hypertension. cardiovascular stiffness, cardiomyopathy, kyphosis, as you can see, osteoporosis, kidney, liver, the fat tissue, the skin, the muscles, all of them show accelerated. They get incontinence, they show stem cell exhaustion, they have overall frail phenotype, they live 4 to 6 months, so they are born, they develop initially, and then they decline very rapidly, and then the maximum life expectancy is about 6 months. I'll show you also later in a moment. So this is the only mouse model, at least the repair mice are the only mouse models that have an accelerated epigenetic clock. So the epigenetic methylation clock of Steve Horvath, as discovered by other people, not even by us, is accelerated. And also in the children with a defect in this pathway have also an accelerated aging clock. And the glycage clock, which is a very different clock, is also accelerated in these mice. So these mice, in all regards, as we can tell, are recapitulating aging, but in a much faster way. So multimorbidity, and this is apparently, if you cannot repair, spontaneous DNA damage can cause all of these aging phenotypes. So this is a very informative model, and particularly we think this mouse is a very excellent model for Alzheimer, for Parkinson, for all aging-related dementias. And I'll show you later. So, what we also found, that we have many mice that, I showed you the ERCC1, I showed you the TTD, I showed you XPA, but we have made many mice, and all of them, all the ones that have accelerated aging, if we look at the activity of all genes in the liver, or the kidney, or any other organ, and compare that with their controls, the wild types at the same age, then you see many differences. And the first difference which we noted was that the mice that show accelerated aging, they suppress the growth hormone IGF somatotrophic axis. And that explains why the mice and these children stay small. They suppress their growth. They use their energy not for growing, but they invest in the antioxidant defenses, in resilience, in all the mechanisms that try to protect you from stresses. And that resembles, so IGF, low levels of IGF explain why cocaine and TTD children stay all very small, and the mice too. But this response paradoxically resembles dietary restriction. If you have less food, the body wisely doesn't waste it in growth, but now uses it to try to survive. So stress resistant, antioxidant defenses become metabolism is redesigned to make you more resilient. So dietary restriction is the only universal intervention that delays aging. So our mice that show accelerated aging, they show a response that looks like delayed aging. So they try to counteract their accelerated aging by suppressing their growth and upregulating all the mechanisms that protect them, that make them survive. We call it survival response. So we now wondered, what would now happen when we put those mice, those mini mice, on a diet? The last thing you would like to do with these small children is to put them on a diet. They get extra food because they have to grow. So, but we wanted to know. And then there was again an eye-opening observation. This is the normal life expectancy of ad libitum mice. So the first mouse dies by the age of 12 weeks, the last one by 27, so they live 4 to 6 months, very reproducibly. And they die mainly from neurodegeneration, like the children. Most of them die from neurodegeneration. So now we put the other half of the mice on a diet. So from week 7, they got 10% less food. Week 8, 20. Week 9 onwards, 30% less. And then looked what happened. And then this happened. So they lived from the moment you put them on a diet 3 times as long. 200% lifespan extension. Normally, in a normal wild-type mouse, 30% dietary restriction will extend lifespan by about 30%. Now this mouse really over-responds. And I'll explain you later why we think that is the case. So there is really, you don't need any statistics we can do experiments with 4 mice, and we see unequivocal difference with dietary restriction in this mouse. So we can reduce mouse costs by a factor of 10, 20 or so, simply by using this mouse. And not only, so median maximum lifespan, 200% lifespan extension. But lifespan extension doesn't mean health span. So we looked at all aging parameters, and no question, unequivocally, all aging phenotypes are delayed in this mouse. I will show you 2 movies, but so the liver, the kidney, the immune system, the vascular system, all of them benefit tremendously from dietary restriction, but most benefit is the neuronal system. The neuronal system is the one where we see expansion of health span 5,000%. I'll show you in 2 movies. So these are 2 littermates, born at the same moment, having the same food and so on. The one on the right is the one that had ad libitum food. I'll show you in a moment. Here you see the food. This mouse, at the age of 16 weeks, barely can walk because it has neurologically already so much declined that it cannot control its muscles. So the neuromuscular junctions are severely affected. It shows these tremors. You see it shakes, and it cannot keep balance. It falls down because neurologically already very deteriorated. Now, on the other hand, the other mouse was on a diet from week 7 and is running around because it thinks, I get food, but can run, no problem, can jump, can make a circle, no problem. I'll show you when you put those 2 mice on a rotating rod and test how they can control their muscles. So the one that was running on the diet, the one that couldn't walk, ad libitum, this is a wild type on diet. And this fat mouse is the wild type that had unlimited of more food. Now, we were the first child, I'll show you, the first child has done this, and I'll show you what happens. So this is Emma. She is a TTD child. You can see it, she's losing little hair. And she is 6 years old. Emma cannot walk, cannot talk, cannot read, cannot write. None of these children can. She received every day 1150 kilocalories directly in the stomach because her appetite is really very low. So Emma, I'll show you, and hope the sound is there too. Yeah, you don't hear the sound that well. But Emma can barely crawl. She shakes like the mice because the neurons cannot control her muscles anymore. She shakes like you see. This is what she barely, and this is progressive. There is no patient that escapes from this because it's progressive, it's DNA damage that accumulates. So then something very worrying happened. Emma got tremors. So you see she starts to shake. So all the muscles, they are not controlled and they take their own rhythm. So, and she could not put 2 Duplo blocks on top of each other anymore. So we know this is very bad prognosis because then she gets paralysis, particularly the legs first and then the hands, and she gets swallowing problems, and then it's finished. So it's a very dramatic disease. So when I have talked to these parents several times already before, and their doctor in France believed our results. So we said, why are we not gradually lowering caloric intake? 1150, go to 1050. If everything goes well, we go to 950 kilocalories or to 850 and see what happens. And we did that. We started 28th of May in 2018. Within 12 days, Emma could build with Duplo again. Her tremors were gone. But we had seen this in mice before. We even saw that paresis, to some extent, can be reverted by dietary restriction. So she could build with Duplo. But then something unexpected happened. Emma started for the first time in her life, at the age of 7, to walk, to keep balance. So that was unbelievable. But it continued. Now you have to listen, because Emma could not talk. She made sounds, but yeah, you could not make out what she means. Now you should listen.
Emma, on fait 1, 2, 3. Allez, on pousse.
Count, pronounce, and make a head over heels. unbelievable for a child that barely could crawl and that has a progressive disease that would only become worse. And now, not only that, she started to write her name, Emma. It's not perfect, but somebody that is, that could not put two Duplo blocks on top of each other, now can take a pencil. She's learning to read. She didn't need diapers. So she can build these constructions. She's on a bicycle. And almost 7 years, 28 this year, she's 7 years older and still doing great. Imagine if we would have started at birth giving her a lower caloric intake. My expectation would be that she would stay small, but she would be quite normal. Even if at this stage we can go back. But we can learn a lot from this, because we can see to which extent is neurodegeneration reversible. It's reversible, and we understand the mechanism. So dietary restriction dramatically improves health, extends lifespan. No way that she would have been alive now, 7 years after already reaching the stage of tremors in 2018. So there is certainly, and now the guidelines globally for all of these children have been reversed, and all parents that we consult, all parents are positive. So it's not N is 1, but it would be unlikely because this mechanism is conserved from yeast to mammals. The mouse, we saw it already, and if we then take the first child, it would be a miracle if this would be N is 1. So anyway, so the first treatment of any repair syndrome, very cheap. It can be introduced globally because it saves you money. Instead of expensive food that it makes the child worse and ill, instead of that you can take less. So it's globally applicable. No, nutraceutical industry is not interested in our research, I have to say. Pharmaceutical industry also not, because simply less food is the solution for these children. But I'll show you what we have learned from these children and why this is important for Alzheimer, for surgery, and for chemotherapy, because these are the next consequences. So, but the mechanism. I could give you another presentation that takes an hour to explain what we found. Let me only give you the take-home mechanism without showing you all the data that we have and that are completely solid and that have been published in Nature Genetics. So what we found is that with aging, you build up damage. And some of that damage happens to be in the transcribed strand of an active gene. Normally, transcription-coupled repair tries to solve that problem, but it's a complicated system that takes a lot of proteins and a lot of energy. And what happens with aging is that many of our cellular systems decline in functionality. So also transcription-coupled repair will decline with aging. And I'll show you why all of these processes become deteriorated, because this is the mechanism that causes it. So we noted that mutants, all the mutants that we have that involve this pathway, transcription-coupled repair, they all have neurodegeneration. There's not a single exception. And the patients do, the mice as well. So this suggests that DNA damage that interferes with transcription somehow causes this neurodegenerative phenotype. So we looked, what happens to transcription with aging? Nobody had carefully looked in organs of aged mice what happens to the basic process of transcription. So we devised a new method, EU labeling, to measure how much RNA synthesis is ongoing when you age, in a normal, not even repair mutant, in normal mice. And we found that transcription goes down. So transcription in our mice first and later in normal mice, we found the same. So it shows that these mice are very important for normal aging because we found this first in our mutant mice. Many people doubt whether they are really aging relevant. We found this phenomenon later in normal mice. So again, something we found first in our mice and later turned out to be present in the wild type aging too. So I'll show you the mechanism. When you are young, there is efficient repair and there is not much damage that blocks transcription. So your transcriptional output is the balanced output that you need for functioning and for growing. So, but with aging, then you accumulate more damage because many of the systems go down, antioxidant defenses go a little bit down, metabolism is less efficient, so you generate more damage. And at the same time, many of those pathways go down because they have a problem, and I'll show you the problem. So you get more damage that accumulates, that takes more and more time to be repaired. But then you can make a prediction. Damage is stochastic. So if you have a long gene, there's more damage in the long gene than in a tiny one. If a gene is 10 times as long, there is 10 times as much damage because it's stochastic. So long genes suffer more than the short ones with aging. So the transcription of a long gene has more trouble because it finds more damages that need to be repaired, and the short gene, hardly any damage. So you get a disbalanced transcriptional output. The long genes go down. And we found that first. Later, other people found it in Alzheimer too, and yet other people with AI found it independently, totally, and were not aware of our findings. So now many laboratories have completely convincingly shown that with aging, long genes go selectively down. And that leads to a disbalanced transcriptional output. Many complexes of proteins, you know, there are protein subunits with a short gene, but other subunits may have a long gene. So the long gene goes down in expression, so you get more incomplete protein complexes. RNA polymerase, TF2H, but numerous complexes have this is genome-wide. So all the genes that are long have the problem when they are expressed. Neurons have the longest genes of all. So that explains also why neuronal degeneration is a hallmark of transcription-coupled repair defect, because the neurons have the longest genes of all. So what we see is a lower, but particularly an imbalanced transcriptional output. And that is really frustrating many cellular processes. Every cellular process that depends on a protein complex will have already a problem, because many, you know, if there is a damage in one of the genes of the subunits, that gene will be lower expressed. So the other subunits are there in the normal amount, but then that one is lacking. So you need to degrade that the unfolded protein response goes up, and we see dramatic upregulation of that. So that explains actually proteostasis is a consequence, nutrient sensing, energy metabolism, cytoprotection, stress response, immune system. All of them are affected by this process. And 50% of all the changes in gene expression profiles with aging, in liver, kidney, particularly in the post-mitotic tissues, the ones that have not much cell renewal, 50% of all the changes can be accounted for by the fact that long genes go down. So it's a dramatic, this has a dramatic effect. So that explains many features that are found with aging in many organs and tissues. And this is not only in mice, it's also in humans. We see it in human data, but even in worms, we see, also C. elegans shows this phenomenon. So it's universal, conserved, and it is affecting many processes gradually, progressively in time. So DNA damage-driven transcription stress explains most aging-related hallmarks in post-mitotic organs and tissues, which actually is the majority of our body is post-mitotic. So, okay. So I'll show you one gene, which is very important. This is the IGF-1 gene. I'll try to finish very quickly. 3 minutes? Okay, well, you see what happens. If you are young, nascent RNA distribution in IGF is the blue line. If you are old, then the red line. So in old, the promoter in old of IGF-1 is higher. You see there is more, the red is higher. There is more transcript in the beginning of the gene. Then, but because there is damage, particularly in this long intron, you see that the red one that is on top of the beginning, at the end is below. And you see that at the very end, there is a dramatic difference between the amount of RNA from the IGF-1 gene, which is a gene that controls growth and that controls aging. IGF, if you suppress IGF, you invest more in maintenance, less in growth, you live longer. The dwarf mice are long-lived mice. So this explains why IGF goes down with aging. So I'll skip a lot of slides. I'll show you that transcription stress also triggers protein aggregation with dementia. So I'll give you a very short outline. So we looked at a protein complex that is aggregating or that is abnormal, building up in 3 dementias: in Huntington, in frontotemporal dementia, and in ALS. So this is a very widespread protein abnormality that occurs in patients. So you can see that this protein aggregation occurs in mice. This is a mouse model. We have not made it. Other people have done that. So you see that they form these aggregates over here, these large blebs. That is RAN gap, the protein that is involved in nuclear transport, export, and import. So it's involved in nuclear transport. So that aggregates with aging in at least three dementias. Now look in our mice. So this, we use the antibodies that in patients also visualize these abnormal aggregates. So that same antibody was now applied to the brains of our mice. And we've taken 2 different mouse models, XPG and ESCC1, to show there's not only one, but there are 2. And you see the same blebs, much more actually, that occur than in patients even. But there is a tremendous aggregation or abnormality of this protein that is normally beautifully decorating the nuclear envelope. And not only that protein is there, we see many other proteins in the same complexes, UBC9, RAN-BP2. We see also RAN, which is another complex, a RAN protein. Not only that, we see also CRM1, which is another protein. In that same complex, we think that complex is also incomplete. So, because there are genes that have a defect in transcription, so you get accumulation of that protein complex too. So that explains why we see protein complex aggregation, actually. And we now find even hyperphosphorylated tau tangles in our mice that have no overexpression of whatever transgene to make the protein much more. No, it's spontaneous itself starts to aggregate. And dietary restriction, that is very important, lowers this, because what we know is dietary restriction lowers your DNA damage. You have more antioxidant defenses. Your metabolism is redesigned. So you make less reactive species. So you make less DNA damage, then you get less transcription stress. If you have less transcription stress, the neurons can make long proteins again. And if you can make long proteins, you can control the muscles better. So that explains why we see this improvement in time. So I'll stop. Well, there are still some other interesting, but maybe I'll show you in the final slide. So hundreds of years of medical research, but in fact, for aging, this is true. Up till now, we do not know how we can influence aging. Dietary restriction is the only universal, very potent, and now we understand much better why, anti-aging intervention. And we can learn a lot from that. And for instance, semaglutide, Ozempic, lowers transcription stress. So we see also there that maybe that will slow down aging. So this is what I wanted to tell you. I'm sorry that I'm over-enthusiastic and over-optimistic, that I think, but you know, I can talk for one day. Thank you.
Right, guys. Ceremony in the plenary area, which is the arena. So if you guys can go.